Hi students, for topic 4 on reactions and stoichiometry, we are basically looking at stuff which most of you, if not all of you, are very familiar with from secondary school. Usually involve calculations centered around mole concepts, balance equations, and probably something which is relatively new, which we'll introduce will be on redox titration. Yeah, and how to actually balance redox equations. Yeah, and also stuff such as acids and bases, because the acids and bases which you encounter in secondary school generally involve acid as a species which ionizes either partially or completely in water to give H plus, and bases you encounter usually are like sodium hydroxide or aqueous ammonia, where they ionize in water either completely or partially to give hydroxide anions. Yeah, so you will notice after some time that this discussion is actually quite limited, because there are more substances which we can view them as acid or bases. It really depends on the model and concepts which we are dealing with. Yeah, so in this particular chapter, we are also looking at the models which can be used to actually classify something as acids or bases. Yeah, these are the learning outcomes in your H2 curriculum. You can go through them on your own. And in particular, we will be describing how to balance redox equations towards the end. Okay, you will also be learning the different ways of balancing redox equation, but I'll probably just be showing you one of the ways where I think it works intuitive and fundamentally correct, which is largely based on electron transfer. Okay, so over at the first section, when we are looking at the formulae of compounds and in 1.1 relative masses, there are several definitions which you need to be familiar with, such as relative isotopic mass, relative atomic mass, relative molecular mass, and relative formula mass. You'll notice that for all the definition, the reference point is always 1/12 the mass of one atom of carbon 12. Okay, the reason why carbon 12 is being chosen as a standard, I guess you can read about it as well, but one of the key reasons is because the mass of carbon 12 has been found to be exactly 12.0000 to the fourth decimal place. Yeah, so therefore it's easier to reference to something where its units or its reference point can be taken as unity. So that is why they use the term 1/12 the mass of one atom, because one atom of carbon 12 is taken to have 12 atomic mass units. So 1/12 will be one atomic mass unit. So that will be the reference point. Okay, yeah. So that's something to take note of. Yeah, I think most of it I don't really need to go through, because these are things which you have learned in secondary school. Okay, so over here for exercise 1.1, you are supposed to calculate the relative molecular and formula mass of the following substances, giving your answer to one decimal place. I'm quite sure every single one of you can do the calculation, but what I need you to take note of is really what they need you to display your answers. Yeah, this is the precision they need you to display your answers to one decimal place. Okay, over here the AR is given to you. So usually this will happen during practicals. Yeah, your lab practices or even your practical exams. Yeah, for your theory paper, you can always reference to the last page of your data booklets. Yeah, so just take note that the first number, the number on top is actually the atomic number, okay, which also represents the number of protons you have in the elements. The number below is the relative atomic mass. Yeah, so this is the number which you should be quoting when you are calculating MR of a substance. Okay, and of course the atomic symbol, I think, is something which you are very familiar with from secondary school. Okay, so over here, I won't go through the calculation in detail, but you have zinc phosphate. So this is zinc 2-phosphate. Yeah, so basically your calculation will involve taking zinc, AR, which is 65.4, multiplied by 3, okay, and then you add it to the AR of phosphorus, 31.0, multiplied by 2, and the AR of oxygen, which is 16.0, and you multiply it by 8. Okay, so if you punch your calculator, you should get 386.2. Okay, so same case for H2C2O4. H2C2O4 is actually what we call oxalic acid. Okay, so this is a very important compound you might want to be familiar with. So its structural formula looks like this. So it has 2 carboxylic acid. Okay, so this is very important because it's a pretty good oxidizing and reducing agent. Okay, so sorry, what am I talking about? It is a pretty good reducing agent. Okay, so it's something which you need to be familiar with. Yeah, so if you do a quick calculation, you should get the AR to be 90.0. Okay, so that's just 1.0 times 2, 12.0 times 2, and then 16.0 times 4. Okay, some of you might be familiar with this. Is glucose formula of one of the kind of monosaccharides. Okay, so again, quick calculation, you should end up with 180.0. Okay, and then this is hydrated copper 2 sulfates. Okay, so again, quick calculation, you should end up with 249.6. Okay, yeah, so please work this out on your own to ensure that you get the correct answers. Okay, so for 1.2, we are looking at percentage composition by mass. Okay, so from the formulae of a compound in a relative atomic mass, the percentage by mass can be easily calculated. Okay, so if we look at exercise 1.2, which of the following compounds, both used as fertilizers, contains the highest percentage by mass? So the highest percentage by mass of phosphorus. Okay, so we can easily perform the calculation by first calculating the MR of each of the substance. Okay, so let's try to calculate the MR of this, the calcium phosphate and calcium fluoride salts. So if you punch your calculator, you should end up with 504.5. Okay, and this ammonium hydrogen phosphate, if you punch your calculator, you should end up with 132.0. Okay, and then after that, we'll calculate the percentage by mass of phosphorus. Okay, so we can easily do that. So in this case, percentage mass of phosphorus. Okay, so that will be 31.0 multiplied by 3 because there are 3 phosphorus per formula of the unknown. Okay, divide by 5045 multiplied by 100%. So 100%. Okay, so we'll end up with 18.4%. Okay, so we'll do the same thing for ammonium monohydrogen phosphates. Okay, so that will be 31.0 divided by 132.0 multiplied by 100%. Okay, so then we'll end up with 23.5%. Okay, so therefore ammonium monohydrogen phosphate has the highest have higher percentage by mass of phosphorus. Okay, so moving on to exercise 1.3. For the first question, you are given the molecular formulae of chlorophyll to be such a huge number, C55, H72, MgN4O5. Ask you to calculate percentage of by mass of magnesium present in chlorophyll. Yeah, so again, you have to punch your calculators. Okay, so please take out a calculator and punch for the MR. So that will be 55 multiplied by 12.0 plus 72 multiplied by 1.0 plus magnesium would be 24.3. Okay, plus nitrogen would be 14. So 14.0 plus 5 times 16.0. Okay, so you should end up with 892.3, okay, as the MR, and then from here the percentage by mass of magnesium, percentage mass of magnesium, okay, will then be equals to 24.3 divided by 892.3 multiplied by 100%. Okay, so you end up with 2.72%. Okay, so I hope you will take out your calculator and just punch in the numbers to see whether you end up with the same answers as what I've written. Okay, so next we'll move on to question 2. Okay, so for question 2, you have hemoglobin, oxygen carrying protein in red blood cell, and it has 4 iron atoms per molecule, contains 0.34% iron by mass. Calculate the molar mass of hemoglobin. Okay, so how do we go about working on this problem? So what we can do is, because you were told that 0.34% iron by mass, okay, so let's say you can let the MR of hemoglobin be A. Okay, then after that, what you can do is 0.34 divide by 100 times A, okay, will be equals to 4 times 55.8. In case you are wondering where to get 55.8, again, data booklet, go to iron, so that's 55.8. Okay, yep. Why is it 4 times? Because 4 iron atoms per molecule. Okay, so we were told that 0.34% of it is due to iron. Yep. Okay, so after that, we'll just transfer the percentages over. So A, you will end up with 6.56 times 10 to the power of 4 grams per mole. Okay, now this is very important because the key word here, which I need all of you to take note of, is the molar mass. Molar mass comes with a unit, which is the mass per mole of the molecule. So it's grams per mole. If the question asks you to calculate the MR of hemoglobin, yeah, the answer will simply be 6.56 times 10 to the power of 4. Okay, so just take note of it. So if they ask for molar mass, so this is molar mass, okay, then it contains a unit. Okay, so I think I need to correct this portion here. It shouldn't be AR, so it should be let the molar mass. Okay, so please correct at your end, let the molar mass, yeah, of hemoglobin be A. Yeah, of course, technically, it is correct if I were to use let the MR. So after that, when I quote A, it will be without the units. Then I can conclude by just saying that, therefore, the molar mass of hemoglobin is 6.56 times 10 to the power of 4 grams per mole. Okay, so it really depends on how you want to draft your answers. Okay, so there is no one standard way, so just take note of it. Okay, so in case you are wondering, let me repeat again. So earlier on, if you let the MR of hemoglobin be A, then your answer will be without the units. But because the question asks you for the molar mass, you still need to conclude by saying that therefore the molar mass of hemoglobin is 6.56 times 10 to the power 4 grams per mole. Yeah, but if at the beginning you already let the molar mass of hemoglobin be A, then you can simply just write A as 6.56 times 10 to the power 4 grams per mole. Yeah, that's it. Okay, so I hope it's not too confusing for you. Yep. Next, we'll move on to 1.3, which again is something which most of you, if not all of you, will be very familiar with. It's on empirical and molecular formulae. Yeah. So based on definition, the empirical formula of a compound is the simplest formula which shows the ratio of the atoms of the different elements. Yeah, so this will be the simplest formula showing the ratio of the different elements. Okay, but for molecular formula, it actually indicates the actual number of atoms of each element. So this is the actual, yeah, which is something which you really need to take note of because they are not synonymous. They are actually different. Yeah, of course, they differ by a common unit, which is N. Yeah, so for example, ethanoic acid's empirical formula is CH2O. So molecular formula will be C2H4O2. But if you look at it, it's actually CH2O2. So the common unit, which is N, is equals to 2. Yeah, then for ethene, it will be 2 as well. So ethene will be CH2. Yeah, but when you write it this way, is actually not the molecular formula. Please take note of it. So let me stress, this is not molecular formula. This is not molecular formula. Yeah, when you write molecular formula, each unique atom can only appear once, and then the subscript will be the actual number of that particular atoms of that elements. Okay, so remember this. When you write it this way, is actually what we call the condensed structural formula. Yeah, or simply just the chemical formula. Yeah, you will learn more about this in organic chem, so not to worry too much. Okay, we'll move on to exercise 1.4. Okay, so these two exercises, 1.4 and 1.5, focuses on the derivation of formulae using composition by mass. Yeah, so very similar to what you learned in secondary schools. So again, please bear with us because when we go through some of these concepts, we need to repeat some of the stuff which you might have already learned in secondary school. Okay, so in exercise 1.4, question 1, we have caproic acid. You are given the MR to be 116. Yeah, so this is MR, not molar mass, although molar mass and MR take the same numerical number. Okay, occurs in goat's milk and has the following composition by mass. Okay, so you are given a composition by mass of 62.1%, 10.3%, and 27.6%. CH and O respectively. Yeah. In most cases, before you perform the calculation, it might be good for you to add them up and see whether you get 100%. Okay, so that will be a good practice. Okay, I mean, if you don't want to do that, it's fine also, but just ensure that they add up to 100%. Okay, so I'll just use the space here. So we have CHO. Okay, so this will be percentage by mass. Okay, then C will be 62.1%, H will be 10.3%, O will be 27.6%. Okay, so this is percentage by mass. And then next we have amount. Okay, so amount is in terms of number of moles. So we'll take 62.1 divided by the relative atomic mass of carbon. Okay, so we'll end up with 5.175. And then hydrogen will be 10.3. Oxygen will be 1.725. And then after that, we'll get the mole ratio. So the mole ratio will be, you divide by the lowest term. Yeah, so in this case, the lowest term is actually oxygen, which is 1.725. So when you do that, you should be able to get 361. Yeah, so in this case, the empirical formula would be C3H6O. Okay, after that, we need to calculate the molecular mass, the relative molecular mass of this particular unit. Yeah, so from here you can calculate MR of C3H6O. So that will be 3 times 12, that's 36. 36 plus 6, that's 42. 42 plus 16, that's 58. Okay, so that will be 58. Okay, then after that, you let the molecular formula of caprylic acid be. So let the molecular, sorry, the pen is not working very well, molecular formula of caprylic acid be C3H6O and then N. Okay, then therefore you can easily calculate N. So N will be equals to 116 divided by 50. Then that will be equals to 2. Yep, then from here you can easily determine the molecular formula of caprylic acid. So that will be C6H12O2. Okay, so I hope it's systematic enough for you to follow, although I did not write out all the working in such a clear manner, but you get the idea how to go about doing it. Okay, then for question 2, you are given 0.4764 grams sample of an oxide of iron was completely reduced by a stream of carbon monoxide to produce 0.3450 grams of pure iron as the only iron containing product. And then you're asked to find the empirical formula of the oxide. Okay, so what you're going to do is again, we can construct a table. So maybe let me use the little bit of space below. I thought that might work a bit better, so that we can use the space over here for exercise 1.5. Okay, so we have iron over here, and then oxygen. And there's only 2 elements in our unknown, because the reason being, if you recall from your secondary school knowledge, when we say that it's an oxide of iron, so that means that your unknown contains only iron and oxygen. Yeah, so I guess some of these fundamental knowledge which you learn in secondary school, you might need to remember them and apply them in the A levels, because they will not be taught again. Okay, and you were told that you have 0.4764 grams of this sample. Okay, so this is the sample of iron oxide, and after reduction you get 0.3450 grams of pure iron. Yeah, so that means that I can easily say that, therefore, right, the mass in terms of grams, right, of the pure iron is 0.3450. And then the mass of oxygen in the oxides of iron will simply be subtracting 0.3450 from 0.4764. Okay, so I should be able to end up with 0.131. Okay, then from here I determine the amount. So basically just divide by the relative atomic mass. So 0.3450 divided by 55.8. I will end up with 6.183 times 10 to the power minus 3. And then for oxygen, I divide by 16.0. I will end up with 8.213 times 10 to the power minus 3. Okay, and then we'll try to get a ratio. So mole ratio. Okay, so we'll divide by the smallest number. So the smallest number here is 6.183 times 10 to the power minus 3. So I will end up with 1 here. And then for the case of oxygen, I will end up with a number very close to 1.33. Yeah, please do not round up, round down, because this is essentially 4/3. So if you multiply by 3, we'll get the simplest ratio to be 3:4. Okay, so therefore the empirical formula of the oxide is Fe3O4. Okay, so I hope the explanation is straightforward enough for you to follow through. Okay, next we move on to question 1 of exercise 1.5. Okay, you are given the formula of a complex salt Z. So that means that the complex salt Z contains different numbers of cations and anions. Yeah. And then the analysis produced the following composition by mass. So you have 15.5% of chromium, 38.1% of sulfur, and 29.2% of nitrogen. So you're supposed to calculate the values of X and Y in the formula for Z. Okay. I think what you might want to do now is to take out your calculator and then you try to add up all the percentages. You realize that they don't add up to 100%. So that's fine because there are some data that are missing. Yeah, but this will not prevent us from getting the correct answer. Okay, the simplest way to do this question, because we are looking at composition by mass in terms of percentage, right, is to begin by assuming that we have 100 grams of salt Z. So if we have 100 grams of salt Z, okay, so if we have 100 grams of it, that means that 15.5 grams are due to chromium, okay, because we have 15.5% of chromium. So if you do a quick conversion from here, you will be able to calculate the number of moles of chromium, and this will be 15.5 divided by the AR of chromium, which is 52.0. Okay, so you end up with 0.2981 mole. Then from here, all you need to do is to do a ratio which is based on the species present. Okay, so what do I mean by that? Okay, so we have chromium is to SCN minus, okay, is to NH3. Okay, so in terms of ratio, that will be for chromium based on the numbers here. So it's 1 is to X is to Y. So that will be 1 is to X is to Y. Yeah, so in terms of the actual number of moles, this will be 0.2981 to 0.2981x, okay, is to 0.2981y. Okay, then from here, we can move on to the next calculation. Because we are given the percentage by mass of sulfur, which is 38.1%. Yeah, so that means that in 0.2981x of SCN, yeah, the mass of sulfur will therefore be 0.2981x, okay, multiplied by 32.1, which is the relative atomic mass of sulfur. And then this will be equals to 38.1 grams. So this is for 100 grams. Okay, so maybe I'll just erase this so that it's clearer. Directly 0.1. Okay, so if we do a quick manipulation, we'll get x to be approximately equals to 4. Yeah, you can easily do a quick calculation on this to verify for yourself. Okay, we'll do the same thing for nitrogen. So for nitrogen, it will then be 0.2981y multiplied by 14.0, which is the AR of nitrogen, and then we equate it to 29. Yeah, so this is for every 100 grams. Yeah, this is the mass of nitrogen. Then we can easily get Y to be 2. Okay, if we do a quick calculation. So that means that we have solved for X and Y in that sense, without actually knowing how much carbon is present and how much hydrogen is present. Okay, so for those of you who are a little bit lost, you can think about it, because I think the calculation for question 1, you need a bit more time to think about. Okay, then moving on to question 2, you were told that on strong heating, 100 grams of calcium sulfate, the hydrated version, so you don't know the number of water crystallization per mole of calcium sulfate, so it's given as N here. is dehydrated and a constant mass of 39.09 grams of anhydrous salt is obtained, they ask you to calculate N. So from here, it is quite obvious that the mass of water lost will then be equals to 100 minus 39.09. So that will give us 20.91 grams. Okay, then from here we can calculate the amount of water molecules in 20.91 grams. So that we 20.91 divided by 18.0. Okay, that will give us 1.162 moles. Okay, and then from here the number of moles of calcium sulfate will then be equals to 79.09, because this is the constant mass remaining, divided by the relative molecular mass of calcium sulfates. That will be 40.0 plus 2.1 plus 16 times 4. So we'll end up with 136.2. Okay, so that will give us 0.581 moles. Okay, and then we'll take the ratio. So in this case, n over 1 is equals to 1.162 divided by 0.581. So we can easily calculate n to be equals to 2. Alright. Okay, so I hope you find the calculation so far manageable. Probably one or two layers more complicated than what you have encountered in secondary school, but I think so far it's still okay, because the more difficult part is actually later on, which is on redox calculation. Yeah, because you'll be learning a new thing on how you could balance redox equations. Okay, yeah. So the next part will be on to derive the formulae using combustion data. So we'll move on to look at exercise 1.6. But do take note that on complete combustion, usually will end, of hydrocarbon, usually will end up with CO2 and H2O. So this is for complete combustion. Usually for incomplete combustion, you end up with some CO and CO2 as well as water. And because it is measured at room temperature and pressure, H2O will exist as a liquid. It will not exist as a gas. So do take note of that when you are performing your calculations. Okay, next we'll look at exercise 1.6. So you were told that on complete combustion of a hydrocarbon, you will get 0.352 grams of CO2. So from here you can calculate the number of moles of CO2, 0.352 divided by 44.0. Okay, so you will end up with, let's try to punch the calculator. Okay, 0.352 divided by 44, 0.352 divided by 44. Okay, you end up with 8.00 to the power minus 3 moles. Okay, and then from here you can calculate the number of moles of H2O. Okay, so you get 0.072 divided by 18.0. Okay, so 0.072 divides by 18. So you end up with 4.00 to the power minus 3 moles. Okay, yep. So you are told to calculate the empirical formula and its molecular formula, given that it has a molar mass of 104 grams per mole. Okay, so well, since you don't know the hydrocarbon, but you know the ratio, so you know the ratio. Let me just write it over here. So you know the mole ratio of CO2 to H2O. Yeah, so that's 8.00 times 10 to the power minus 3 is to 4.00 times 10 to the power minus 3. Yeah, so you get 2 is to 1. Yeah, but from here, the number of moles of carbon to the number of moles of H. It's not 3, it's not 2:1. Yep, it's actually 1:1. Why is that the case? Because for 1 mole of water, there are 2 H's. Yeah, okay, so based on that, the ratio of carbon to hydrogen is 1:1. So therefore, the empirical formula, you can easily calculate it to be, or determine it to be from here directly, to be CH. Yeah, so CH is the empirical formula. So just take note. Okay, CH is the empirical formula, which you should write as your answer. Then 1 unit of CH, so the MR of CH is basically just 12.0 plus 1, so that's 13.0. Okay, and because you were being told that the molar mass is 104 grams per mole, so therefore, if you let the molecular formula, okay, so if you let the molecular formula be CHN, so therefore N will be equals to 104 divided by 10. So you should end up with 8. Yeah, so therefore molecular formula is equals, the molecular formula is C8H8. Yeah, please take note that you cannot write your molecular formula as CH bracket N, or rather CH bracket 8 is incorrect. Although in our case here it is okay, because it still denotes the number of atoms for carbon and hydrogen in a relatively unambiguous manner. Yeah, okay. Now we'll move on to 1.7. So for 1.7, you have X is an organic ion compound containing only iron, carbon, and hydrogen. And then when a sample 0.944 grams was subjected to complete combustion, you get 2.23 grams of CO2 as well as 0.457 grams of water. So again, actually the concept is the same. After a while, you realize the way to do it is actually quite similar. Yeah, so you have to deal with the mass of CO2 given, and then sometimes, of course, the mass of water given. Okay, so from the mass of CO2 given, you can calculate the number of moles of CO2. Okay, and from here it will be 2.23 divided by 44.0. Okay, so quickly take out a calculator and punch in the numbers. So that will be 2.23 divided by 44. Yeah, so we'll get 0.05068 moles. Okay, then we'll do the same thing. Okay, for the number of moles of water. So number of moles of water will then be equals to 0.457 divided by 18.0. Okay, so we'll get 457 divided by 18. So we'll get 0.02539 moles. Okay, after calculating the number of moles of CO2 and H2O, what we will do is we will determine the mass due to carbon and hydrogen. Okay, so therefore mass of carbons present will be equals to 0.05062 multiplied by 12.0. Okay, so if you take your calculator and punch in the numbers, let me just punch in the numbers. So 0.050682 multiplied by 12. So I will be able to get 0.6082 grams. So this is the mass of carbon. Then the mass of hydrogen will then be equals to 0.025389 multiplied by 1.0. multiply by 2. Why multiply by 2? Because for every 1 mole of water, there's 2 moles of hydrogen. Okay, so from here we'll do the same thing, 0.025389 times 1.0 times 2. Okay, so we'll end up with 0.05078 gram. Okay, then with these two data, we can easily determine the mass of iron present. So the mass of ions will then be equals to 0.944. So that is the mass of the sample of X. Okay, minus 0.6082 and minus 0.05078. Okay, so we'll just quickly calculate. My apologies because I haven't calculated it early on. Minus 0.6082, okay, and then minus 0.05078. Yeah, so you end up with 0.285. So 0.2850 grams. Okay, then from here you can easily perform the ratio. If you then you can easily determine the empirical formula. So what should we do to determine the ratio? So we will just have iron, carbon, and hydrogen. Yeah. So for iron, you know that the mass is actually 0.2850. For carbon will be 0.6082. For hydrogen will be 0.05078. Okay, then we'll determine the amount. So the amount will of course be similar to what we have earlier on, which is these two numbers. Okay, so but of course we can just follow through the calculation and then we'll see what we get. Yeah, then of course for iron 0.285, so this will divide by 55.8. Okay, so this is the mass and then this is the amount. Okay, so you end up with 0.005108. And then for carbons, 0.6082 divided by 12. So I end up with 0.05068, same number. And then for hydrogens, it's the same, 0.05078. Okay, so if you just follow through the numbers, you realize that they are pretty similar, except that carbon and hydrogen, the amount is 10 times more. Okay, so the simplest ratio you get will be 1:10:10. Okay, so therefore from here you can conclude that the empirical formula of X is iron C10H10. Okay, next we'll move on to section 2. So over here is something which you are also familiar with, reactions and stoichiometry. So basically just more concept. Okay, so we'll go straight to 2.1. It's law of conservation of mass. So a chemical equation represents what happens during a chemical reaction. So just make sure that your equation is balanced, because if it's unbalanced, that means that you are not able to account for the atoms present in the molecular formula of your unknowns. Okay, so in this case, for exercise 2.1, you are asked to write a balanced chemical equation for the following reaction. So you have lead plus silver nitrate. So you get lead nitrate plus silver. So this should be fine. If you are unsure the formula, I mean the chemical symbol for lead and silver, you can always go to the data booklet over here. So I thought it's quite straightforward. These are some of the elements you need to know. Yeah, so silver is Ag, stands for argentum. Then lead is Pb, which stands for plumber. Yeah, it's good to know, but if you don't know the Latin name, it's fine also. Okay, so we have lead Pb plus silver nitrates, AgNO3. Okay, Ag exists as a positively charged cation, so AgNO3. Yeah, and then along the way you get lead nitrate. But you know that lead exists as 2 plus and nitrate is minus, so we're going to have NO3 2 here. So if there's a 2 here, I will need 2 silver, and then of course plus 2 Ag. Yeah. If you scrutinize the equations which you have written, essentially you have written a simple redox equation. The reason is you will notice that the spectator ion is actually nitrate. So nitrate simply just floats around the solution and it does not participate in the reaction. So what exactly happened here is that let's transfer 2 electrons to silver. Okay, yeah, so let's having transferred 2 electrons to silver, right? So it will end up with +2 oxidation states, aqueous, and then of course along the way then my silver will be precipitated out as a solid. Yeah, so one of the fundamental thing, later we will be talking about it, when you balance redox equation, is that the charge on both sides must balance in addition to the material. Okay, so if the total charge on the left is 2 plus, the total charge on the right must be +2. Yeah, of course, material balance is also important. So I have 1 lead here, I also have 1 lead here. I have 2 silver here, I also have 2 silver on the right hand side. Okay, so basically you have written a simple redox equation without knowing it. For question 2, what you have is iron 2 chloride. So iron 2 chloride will be FeCl2 plus chlorine, and then you end up with iron 3 chloride. So that is FeCl3. Yeah, so if you simply do a quick balancing, you will just be half moles of chlorine, which we are talking about. Okay, but of course, if you wish to multiply by 2 on both sides, that is fine also. So if you multiply by 2 on both sides, that will be 2 FeCl2. You end up with 2 FeCl3 on the right hand side, and then the total amount of chlorine balances as well. Yeah. If you scrutinize the above, this is also a simple form of a redox equation which you have written out unknowingly. Yeah, because in this case, chloride is the spectator ions. Chloride is not involved. Yeah, and chlorine on as one of the reactant is actually the oxidizing agents. So we have iron 2 plus here being oxidized by chlorine. Yeah, so in this case, the iron 2 will transfer 1 electrons to chlorine, and in the process, I will produce 2 equivalent of iron 3 plus, and I will end up with 6 chlorides. Okay, okay, in this case, is 2 Cl minus, because I did not write the spectator ions from the iron 2 chloride. Yeah, then remember earlier on what I have tried to show you, the fundamental ideas behind redox balancing. The charge must balance, right? So the total charge on the left hand side is +4, so 2 plus times 2, that's +4. The total charge on the right hand side is 3 plus times 2 plus 6 plus minus 2. Yeah, so you end up with +4 as well. So that's a perfect balance equation. Okay, yep. Then next we'll move on to exercise 2.2, where you are given a mixture of copper sulfate, 5 water of crystallization, and magnesium sulfate with 7 water of crystallization. You heat it until a mixture of anhydrous salt is obtained. Okay, then you are given 5 grams of the mixture, and then you were told that 5 grams of it, you end up with 3 grams of the anhydrous salt. Then they ask you what is the percentage by mass of copper 2 sulfate dot 5H2O in the mixture. Okay, now what is very important here is the information. You are given 5 grams of the mixture, and eventually you end up with 3 grams of the anhydrous salt. Yeah, so that actually means that in the process, some amount of water is being lost, which you will need to determine along the way. Okay, so if we start by, okay, one of the ways to do this particular question is you probably want to let the unknown amount of copper 2 sulfate be X, and then the unknown amount of this be Y. Okay, that is the usual strategy that people will employ. But once you introduce X and Y, you notice that it kind of complicates matters a little bit because you have two unknowns. So where possible, right, we will try to simply work with one unknown so that it allows us to solve our problems in an easier manner. Yeah. So in this case, I will not attempt to use X and Y here. So even if I were to use X and Y, I will simply be letting the mass of copper 2 sulfate be X grams, for example. And therefore, the mass of magnesium sulfate dot 7H2O will simply be 5.00 minus X grams. Yeah, you notice that when I do it this particular way, right, I avoid introducing another variable. Okay, then from here, you will also notice that what you can do is if I use the number of moles of copper 2 sulfate, if I were to try to determine the number of moles of copper 2 sulfates, that will simply be X, okay, divided by copper will be 63.5. Let me just do a quick check. 63.5. So that's 63.5 plus 32.1. That would be sulfur plus 16.0 times 4. Okay, so and then I have 5 water here, so that's water is 18, so that's 5 times 8. Yeah, so this will be the number of moles of copper sulfate dot 5H2O I have. So you will notice that if this is the number of moles of copper sulfates dot 5H2O, so I will use a different ink, dot 5, sorry, copper sulfates dot 5H2O, right? So if I'm going to hit it very strongly, okay, then the question you want to ask yourself is, what is the amount of copper sulfate I will obtain at the end of the day? Yeah, I don't know whether it's agreeable, but this will be the amount, right? So I'm just going to box out in red. So this will be the amount of copper sulfate I have at the end of the day, which exists as solids. Okay, so this is solid. And then plus, if you can agree with me, 5 equivalents of the one I'm boxing up in H2O. Okay, and of course, these will be lost as gas. So be lost as gas. Okay, so take a while to think whether you agree with my logic. Okay, so the same logic will apply to magnesium sulfates. So I'm just going to write it below in orange. So that will be 5.00 minus X divided by, so magnesium will be 24.3. So that will be 24.3 plus 32.1 plus 16.0 times 4 plus 7 times 18. Okay, then this is the amount of magnesium sulfates dot 7H2O. So this is solid. So again, I heat it. Okay, so again, if I'm going to cloud this part, okay, so this is the amount. So the amount of anhydrous magnesium sulfates I'm going to get is like this, MgSO4 solids. Okay, and then plus 7 equivalents of H2O gas. Okay, because they are being lost as steam. The next thing we want to do is to sum up all the numbers we have written here. I think it's easier. So we just need to punch our calculator, 63.5, 32.1, 16.0 times 4, and then 5 times 18. Okay, so we'll end up with 249.6. Okay, then we will also be summing out all this 24.3 plus 32.1 plus 16.0 times 4 plus 7 times 18. So we'll end up with 246.4. Okay, it will be good to sum up the mass, the MR of the anhydrous salt as well. So let's try to do that. Okay, so when we try to sum up for copper sulfate, that would be 63.5 plus 32.1. 63.5 plus 32.1 plus 64. So we end up with 159.6. 159.6. Okay, we'll do the same for magnesium sulfates. That will be 24.3 plus 32.1 plus 64. 120.4. Okay, why are we doing this? Because we are being told that at the end of the day, we will get 3 grams of the anhydrous salt. Yeah, so this is a very big clue which you need to be aware of. 3 grams of the anhydrous salt. Okay, so with that particular clue, can I then say that the 3 grams of the anhydrous salt is made up of the anhydrous copper sulfates? So that will be X over 249.6 multiplied by 159.6, okay, plus 5.00 minus X over 246.4 multiplied by 1204. Okay, so from here, one equation, one unknown, we solve for X, which if you do a quick calculation, 3.69 grams, because X is actually the mass of copper sulfate dot 5H2O. Then you are supposed to determine the percentage by mass. So therefore, percentage mass by mass of dot 5H2O is equals to 3.69 over 5.00 times 100%. So from here we'll get 73.8%. Okay, so I hope you can understand what exactly we have discussed over here, although it might be a little bit challenging for some of you, but do take a bit of time to go through the steps again and then understand the solutions. Okay, then of course here we have the laws of conservation of by mass. It can be shown by this particular experiment. So what we do here is we have lead nitrate and then lead iodide in the conical flask. Okay, then when we mix the two solutions together, we will get lead iodide as the solid PBT. And then after that, what we will do is we'll reweigh the conical flask and the contents. And then the total mass should be the same as the initial mass. So this is how you prove the laws of conservation of mass. 2.2 is also something which is not new to most of you. It's what we call limiting reagents. So a balanced equation actually showcases the mole ratio, the number of moles where they react. So for example, in the combustion of H2 by oxygen, you get H2O. So the mole ratio for hydrogen to oxygen to water is 1 is to half is to 1, or you can say that it's 2 is to 1 is to 2. So that means that um, every 1 mole of H2 will give 1 mole of H2O, and it must react with half a mole of oxygen at least. Anything less, then the amount of product will be dependent on the amount of oxygen. So that's what we call the limiting reagents. Okay, anything in excess is what we call the excess reagents. Okay, and then in most real experiments or experiments performed in the lab, you expect certain amounts of products produced, but normally you don't get that particular amount. So the expected amount of product produced is called the expected mass, and then from there you can calculate the theoretical yield. So for example, if you're expecting 10 grams and you're only getting 9 grams, so that means that your actual yield of the experiment is 90%. Okay, because it's less than what you expect. You will not get more than 100%. That's ridiculous. So usually when that happens, that means that either the sample, if you are doing it in aqueous medium, is not dry enough, etc., etc., or there might be other side products being formed which you might not be aware of. Yeah, so it's almost impossible getting a yield of more than 100%. Yeah, so it is of utmost importance for you to determine the reactants in excess, and of course the limiting reagents as well in any of the stoichiometric calculations. You will encounter them largely in the practical setting, so it's important for you to be familiar on how to go about determining them real fast. Okay, then the The next portion is on the types of reaction. We wrote here as background information. It is really for you to be aware that most of the simple reaction you have learned thus far can be classified into a few categories. So in the first category we are looking at is what we call precipitation reaction. So for precipitation reaction is where you produce a precipitate. So in this case, silver chloride precipitate is being produced from the reaction of silver nitrate and sodium chloride. And then for the next reaction, you are producing barium sulfate, which is an insoluble salt from sodium sulfate and barium nitrate. So this is known as precipitation reaction. Some people will call it displacement reaction, so they mean the same thing. For thermal decomposition, you might really want to take note of this because most of students will get confused. This simply means that the compound itself undergoes a chemical change and break down into smaller components. This is not combustion. Maybe I write in red. This is not combustion. Okay, remember this. Combustion, you will require oxygen. Thermal decomposition simply occurs when you introduce heat to the system, and then the structure, it can be an ionic compound or it can be a covalent compound. It breaks down to give you something smaller. Okay, so please take note of this. Thermal decomposition is not combustion. Yeah, quite a lot of students have misconception in this. Acid-base reaction basically between acids and bases. So it can be, later on we'll introduce you to Bronsted acid and bases, Bronsted-Lowry acid base, and then Lewis acid base. And then redox reaction, you have seen a simple example earlier on. Usually it involves electron transfer. Okay, and redox equation usually involve oxidation and reduction. Okay, most of the reaction which you will learn in A levels will fall into one or more of these categories. So, as I mentioned earlier on, there might not be a need for you memorize them at this stage. So once you encounter them, just take note of them, and then you can move on from there. Yep, and then if there's anything you're unclear about, do clarify with our teachers. Okay, then in the following sections, we will see calculation involving some of these ideas like reacting masses, volume of gases, and then volumes and concentration of solutions. So again, before we go through the practices, the exercises, do go through them on your own first. Okay, I think that will help a lot. Okay, so for exercise 2.3, the first question actually involves reacting masses. So first, you have solid aluminum sulfide. Before you do anything, please uh, know how to write the molecular formula. Yeah, so aluminum sulfide, aluminum is 3 plus, sulfide is S2 minus. So molecular formula would be Al 2 S3. Okay, so remember this. And then reacts with water to give aluminum hydroxide. So please know how to write formula for aluminum hydroxide, AlOH3. And then hydrogen sulfide is H2S. Okay, anyway, you are given this. Okay, it will be good for you to write a balance equation first. So if you take a look at the question, this asks you to write a balance equation for these reactions. So let's try to do that. Okay, so we'll try to write the balance equation on top. Okay, so we have Al2S3 solids, so you are given solids, plus H2O liquids. Okay, so usually we leave a bit of space here for you to write the coefficient and an arrow, and then AlOH3 solids plus H2S, which is a gas. Okay, the easiest way to do balancing over here, right, is simply just to take a look at the coefficient of the unique components. Okay, so we have 2Al here, so that would be 2AlOH3. Okay, and then we have 3 sulfur here, so likely to have 3H2S. Yeah, so then we look at the right hand side to look at the ratio of hydrogen to oxygen. So 3 times 2 we have 6H, 3 times 2 we have 6H as well. So we have a total of 12 H's and then 6 oxygen. So that means we have 6H2O. So this will help us to balance. Okay, so you are being asked what is the maximum mass of H2S that can be formed when 158 grams of aluminum sulfide reacts with 131 grams of water. Okay, so what we can do here is first of all, let us calculate the number of moles of aluminum sulfide. So from here, the amount of Al2S3 would be 158 divided by the MR. So that would be 2 times 20 Okay, so we will get 1.05 moles. Okay, then we'll try to find the same thing for water here. So 131 grams of water. So from here, the number of moles of water will be equals to 131 divided by 10 0. So that will give us 7.278 moles. Okay, then depends. What you can do is you can simply just multiply this number by 6, and then you realize that Al2S3 is the limiting reagent. Okay, or you can simply divide 7.278 by 6, then you will realize that you do not have enough aluminum sulfide to react with it. So therefore, Al2S3 is the limiting reagent. So no matter which perspective you want to take, you will get the same answer. Yeah, not to worry about it. Yeah. So from here, you will be able to conclude that. So Al2S3 is actually the limiting reagent. Yeah. So in this case, I will be able to calculate the maximum mass of H2S, and I will base it on 1.051. Okay. So max mass of H2S is simply 1.051 multiplied by 3 multiplied by the AMR, that will be 2 plus 32. So from here, I will be able to get 108 grams. Okay, then you are asked in a relatively interesting way, although in most cases we don't ask a question like this, calculate the number of moles of the excess reagent remaining at the end of the reaction. Okay, so from here we can calculate the amount of water remaining. So this will be 7.278 multiplied by 1.0516. Okay, so I should be getting 0.972 moles. Yep, I think we have solved every single bit of this problem. Okay, so next we'll move on to question 2. You have 41.5 grams of tungsten 4 oxide, so tungsten 6 oxide, so WO3 reacted with excess hydrogen gas, so you get metallic tungsten and 9.50 cubic centimeters of water. So you are supposed to find the mass of tungsten produced and its percentage yield, given that the density of water is 1 gram per cubic centimeters. Okay, so as per all question, it will be excellent if you can write a balanced equation first. So we have tungsten oxide as a solid, and then it's reduced by excess hydrogen gas. We don't know how much hydrogen, but it doesn't really matter over here. And then in the process, I'm going to get tungsten solids, okay, and water as H2O, so that will be H2O liquids. Yeah, so again, we have 3 oxygen on tungsten 6 oxide. So in this case, I will need 3 H2 to balance it out. Okay, then from here, from the 9.50 cubic centimeters of water being formed, we can easily convert it to mass. So that would be 9.50 grams of water being formed. And then we can easily calculate the amount of water being formed. So the amount of water is therefore equals to 9.50 over 18.0. Yeah, so that will give us 0.5278 moles. Okay, then from the amount of water being formed, we will be able to determine the amount of tungsten I have. Okay, or rather the amount of tungsten octanes, because tungsten to water is in a 1:3 ratio, so it's shown here. So it's a 1:3 ratio. Yep. So from here, I will be able to determine the amount of tungsten being produced. So that will simply be 0.5278 divided by 3. So I will get 0.1759 moles. Okay, then in terms of the mass, so the mass of tungsten will be 0.1759 multiplied by tungsten will be over here. Tungsten, where is tungsten? Tungsten, yeah, it's here, tungsten. So that's 183.8. Okay, so that will be 183.8. Okay, so we'll take out the calculator to determine. Okay, so that will be 0.1759 multiplied by 183.8. So I'm going to get 32.33 grams. Okay, then earlier on we were told that 41.5 grams of tungsten oxide was reacted with excess hydrogen gas. Yeah, so from here, we should be able to determine the amount of tungsten oxide used. So that would be 41.5 divided by 183.8 plus 16 times 3, so that's 48. Okay, so again, we'll take the calculators to calculate quickly. 183.8 plus 48. So this gives us 231.8. So this is 231.8. So we'll take 41.5 divided by 231.8. Okay, so we are going to end up with 0.1790 moles, which is also the theoretical number of moles of tungsten I should obtain. Theoretically. Okay, number of moles I should obtain theoretically. Okay, then from here I can calculate the theoretical mass of tungsten obtained. Okay, that will be 0.1790 multiplied by the AR, which is 183.8. Okay, so we'll do a quick calculation on that. Multiply by 183.8, we'll get 32.906 grams. Okay, so from here we can determine the percentage yield. Okay, so the percentage yield will be equals to 32.33 divided by 32.906 times 100%. Okay, so we'll try to do that. 2.906. Okay, so we'll get 98.2%. 98.2%. Okay, not too shabby, so that's a whooping 98.2% yield. Okay, so that's really good. Alternatively, you do not need to convert to mass. You can simply work in terms of number of moles. So you can simply use 0.1759 divided by 0.1790 times 100%. So you should get the same answer. Okay. Then for exercise 2.4, so we have 18.5 grams of methane and 43.0 grams of chlorine. Gas undergoes the substitution reaction that has an 80% yield. So we'll find some space to write out the balance equation. So they ask what mass of chloromethane is obtained other than HCl. So again, we'll try to write a balance equation. So that's CH4 plus Cl2. You get CH3Cl plus HCl. Okay, so all the information is given here. Okay, so they ask you what is the mass of chloromethane obtained. You were told that is 80% yield. Okay, so we'll do this relatively quickly by focusing on the MR. Okay, I mean not the MR, sorry, the amount. So we have 18.5 grams of methane. So we can calculate the number of moles of methane by taking 18.5 divided by 16.0. So from here we can get 1.56 mole. Then from the 43 grams of chlorine, we can also determine the amount of chlorine, which is 43.0 divided by 71.0. That's 0.6056 moles. So you know that methane and chlorine react in a 1:1 ratio over here. So you know that chlorine is therefore the limiting reagent. So this is limiting. Okay, if this is limiting, then you can easily determine the amount of chloromethane formed. So this will also be equals to the amount of CH3Cl formed. Okay, and because you were told that the yield is 80%, right? So you need to scale it by 80%. So therefore, the actual mass, of CH3Cl will then be equals to 0.6056 multiplied by 0.80, because that's 80%, and multiplied by the relative molecular mass of chloromethane. So that would be 50.5. So you will be able to get 24.5 grams. Okay, so this will be the mass of chloromethane produced in the course of the reaction. Okay, so the next section we're going to move on to is 2.5, which is based on the calculation using volumes of gases. In topic 3 under gaseous states, you learn about the Avogadro's law, which basically states equal volumes of gases under the same temperature and pressure contains the same number of particles. How do we prove it? Of course, we assume ideal gas behavior, so PV equals to nRT. You make volume the subject of the equation, so V will be equals to N RT over P. Yeah, so given the same temperature, okay, and the same pressure, and you know that R is a constant, so that means that volume is directly proportional to amount or number of moles. Yep. So in that case, you know that the volume is actually a proxy to the number of moles. Yeah. So as mentioned over here, volume ratio is also equals to mole ratio. Okay. So for example, you are given this equation involving the combustion of CO. So you are given 20 cubic centimeters of CO reacts with 10 cubic centimeters of oxygen to give 20 cubic centimeters of carbon dioxide. In terms of stoichiometric ratio, we will say that 2 equivalent of CO reacts with 1 equivalent of O2 to produce 2 equivalents of carbon dioxide. In terms of number of moles, we will say 2 moles of CO reacts with 1 mole of oxygen, giving 2 moles of CO2. Based on Avogadro's law, this in terms of volume is also correct. So 20 cubic centimeters of CO will react with 10 cubic centimeters of oxygen, giving 20 cubic centimeters of carbon dioxide. Okay, so do take note of this. Yeah, so if you are simply given the volume information, then that's fine because you will end up with 2 to 1 to 2 ratio. Okay, yeah, and you get to learn a new variable here, which is what we call the molar volume. So do take note of this term, the molar volume. So this is the volume occupied by 1 mole of gas at a specified temperature and pressure. Okay. For the H2 curriculum is actually defined for you. Yeah. So there are 2 conditions which you need to be familiar with. The first one is standard temperature and pressure, short form STP. Okay, so please do not get confused. The short form is STP. Temperature is defined as 273 Kelvin or 0 degrees Celsius. Pressure is 1 bar or 100 kilopascal or 1.0 times 10 to the power 5 Pascal. The molar volume is a fixed value, 22.7 dm cube per mole. Okay, so 1 mole of any gas at STP will occupy 22.7 dm cube. Okay, the next condition you need to be familiar with is room temperature and pressure, short form RTP. Okay, so RTP will be the short form over here. So do take note of this. Temperature is defined as 293 Kelvin. Okay, so that's 20 degrees Celsius. Yeah, so do take note of this value. Is different from what you might be familiar with, which is 25 degrees Celsius or 290 Kelvin. Okay, pressure is 1 atmosphere, which is defined as 101,325 Pascal. Okay, you might need to know the exact value. And molar volume defined as 24 dm cube per mole. Okay, is there a need to memorize this? the answer is no, is actually in your data booklet. So if you look at your data booklet, you flip over to the second page. Okay, so this is the first page of your data booklet. So you flip over to the third page. Okay, you are given some important values and constants. So the first one is the molar gas constant, which would have been highlighted to you in the topic under ideal gas. Faraday constant, you will learn it in electrochem. Avogadro constant, you learn that since secondary school, and then the Planck constant, speed of light. Okay, so we are interested in molar volume of gases. Okay, so do take note, this STP is defined as 10 to the power of 5 Pascal or 1 bar, 273 Kelvin. Okay, molar volume 24 dm cube per mole, and you need to know the exact value 101325. So that's 1 atmosphere and then 293 Kelvin. Okay, so you might just want to update this. 101 kPa is not good enough, so you need to know the exact values. Yeah, okay, so we're going to move on to the next part. Okay, maybe before that, some students have issues with unit conversion for volume. For example, you are not sure when you convert cubic centimeters to dm cube or cubic meter, should you multiply by 10 to the power 3 or should you multiply by 10 to the power 6? Okay, so let me just share something which I learned in primary school, during my primary school education with you. So if you imagine a cubic volume, so you draw a cube out. So this is a cube. Okay, so you draw a cube with dimension 1 cm. Okay, so this is 1 cm by 1 cm by 1 cm. Okay, so the volume of this cube will be 1 cubic centimeters. Okay, so back then my teacher taught me that if you want to convert to, let's say, cubic meter or dm cube, you just need to convert the individual dimension. So 1 cm, let's say we're going to convert to cubic meter. So 1 cm would be 10 to the power of minus 2 meters. Okay, so this will be 10 to the power of minus 2 meters. So this will be 10 to the power of minus 2 meters. Okay, so therefore 1 cubic centimeters is equals to 10 to the power of minus 2 to the power of 3. So this is equal to 10 to the power of minus 6 cubic meter. Yeah, so if you learn how to convert this way, you don't have to memorize all these little things. Yeah, so there isn't need to put them into memory. Okay, next we'll move on to exercise 2.5. So for exercise 2.5, question 1, you are given a mixture of 10 cubic centimeters of methane, 10 cubic centimeters of ethane. They were sparked with excess oxygen. Then after cooling to room temperature, the residual gas was passed through aqueous potassium hydroxide. You might be wondering what is the purpose of aqueous potassium hydroxide. Okay, so it is really to absorb CO2. Yeah, so this is to absorb acidic gas. Yeah, such as CO2. Okay, so the question actually asks what volume of gas was absorbed by the alkaline. Okay, so because you have a mixture, it will be extremely useful if you can write a balanced equation for them separately because it's more correct that way. Because if you involve methane and ethane in the same equation, you might be giving the signal that methane might react with ethane. Okay, so if we write the balanced equation, we will have CH4 methane, which is a gas, plus excess oxygen. Do take note that when they say excess, your product is CO2 only. There's no CO. Okay, then plus 2H2O liquid. Yep, and then you can quickly do the balancing. So that's 2 here. Okay, and you do the same for ethane. So that's C2H6 gaseous plus O2 gaseous, and then arrow. You have 2 CO2 gaseous plus 3H2O. So altogether 7 oxygen, so that would be 7/2. Okay, so the total volume of methane used is actually 10. So remember earlier on you learned that volume ratio is the same as mole ratio. So since we are using 10 volume of methane, and this is a 1:1 ratio, so I would expect 10 cubic centimeters of CO2 to be produced from here. Okay, so 10 cubic centimeters of CO2 from methane over here. Okay, and from ethane, because I'm given 10 cubic centimeters of ethane as well, so I expect 20 cubic centimeters of CO2. Yeah, so therefore the total volume of CO2 evolved or produced, which is also the volume of gas absorbed by the alkaline, you basically just sum up 10 and 20. So you will get a total volume of 30 cubic centimeters. Yep, so in this case, the answer is 30 cubic centimeters. Okay, I hope that is straightforward enough. Okay, next we'll move on to question 2 of exercise 2.5. So we have 100 cubic centimeters of gaseous hydrocarbon W. You burn it in 500 cubic centimeters of oxygen. Okay, and then you notice that 50 cubic centimeters of oxygen is left unreacted, while 300 cubic centimeters of CO2 and 300 cubic centimeters of steam are produced. Okay, so do take note that the condition is slightly different from what you encountered earlier on. All gases are measured at 150 degrees Celsius and 1 atmosphere. First, I think we need to deduce the balance equation for the reaction. So it would be easier if we simply let the hydrocarbon be CXHY. So let W be CXHY. So let us try to write a balance equation in the form of X and Y. Okay, so we have CXHY, which is a gas, plus oxygen. And you notice that CO2 is only dependent on X, and H2O is dependent on Y. So in that case, we will have X CO2 gases and plus H2O. We were told that this is not done in standard condition, 150 degrees Celsius, so H2O will exist as steam. Okay, and because we have YH here, so over here the stoichiometric coefficient will be Y over 2. Okay, so do take note of this. I think I stressed this earlier on. So this is dependent on Y and this is dependent on X. Okay, and if we were to sum up the oxygen, we will have XO2 here. Okay, and then Y over 2O, but in terms of O2, that will be Y over 4O2. Okay, so that will be a total of X plus Y over 4 oxygen. Okay, so I hope this is clear enough how to write the balancing. You do not need to memorize this balancing equation. I think some textbook, most textbooks will have this, because you can easily derive that this expression in exams. And do take note that it is not always that you'll be given hydrocarbon. Sometimes you'll be given maybe CXHYOZ, something like that. So the compounds may contain oxygen. Yeah, if it contains oxygen, then you need to rewrite the balance equation. So that might pose some challenge if you were to simply just memorize. Okay, so suggestion is just derive it when you need to use it during exams. Okay, yeah. So after we write this balance equation out, how are we going to derive the molecular formula of W? Okay, so right now we'll just look at the information given to us to help us work through the problems. First, we need to look at the volume given. So we have 100 cubic centimeters of W, 500 cubic centimeters of oxygen. That's at the beginning, and then at the end of the day we have 50 cubic centimeters of oxygen remaining, 300 cubic centimeters of CO2 produced, 300 cubic centimeters of steam produced. Okay, so what we're going to do here is, I think first it will be easier if we just write initial volume. So that's VI in terms of cubic centimeters. Okay, so earlier on, if you remember that this will be 100, oxygen will be 500, CO2 and steam will be 0, 0. Okay, then final volume. So final volume. So you were told that this is burned, the hydrocarbon is burned in excess oxygen. Then obviously you assume complete combustion, so you have 0 for your hydrocarbon. And you were told that 50 cubic centimeters of oxygen remains, so you write 50 here. And you were told that 300 cubic centimeters of CO2 is produced and 300 cubic centimeters of steam is being produced. Okay, then the next part will be crucial. You need to write out what we call reacting volume ratio. So I'll just represent it with reacting volume. So there are different ways to represent this, but basically this represents how much react with how much. Okay, so for the case of the hydrocarbon, there will be 100 cubic centimeters reacted with 450 cubic centimeters of oxygen. In the process, produces 300 cubic centimeters of CO2 and 300 cubic centimeters of steam. Okay, so in terms of the ratio, the simplest ratio, this will be 1 is to 4.5 is to 3 is to 3. Okay, then you will notice that from the above, you can straight away, okay, be able to conclude that x is therefore 3 and y is therefore 6. Okay, I think from here is pretty straightforward, right? So therefore the hydrocarbon formula, so W formula will be C3H6. Okay, if we were to write out the balance equation, that will be C3H6 plus 9 over 2 oxygen. Okay, then you get 3 CO2 and 3 H2O. Okay, so I hope that will be relatively straightforward for question 2. Okay, so next we'll look at question 3, which is a little bit more difficult. Okay, you notice that question 2, right? You were told that all the gases were measured at 150 degrees C. For question 3, you notice that all volumes are measured at RTP. Yeah, so this actually adds a layer of difficulty to the question. And in addition, okay, let us read through the question first. You have 10 cubic centimeters of gaseous hydrocarbon exploded with excess oxygen. You get a contraction of 20 cubic centimeters after the combustion. Yeah. So this statement, you need to learn how to interpret what we mean by there's a contraction or there's an expansion. Okay, yeah. So it depends on the nature of the question. Okay, and then the next statement you also need to learn how to interpret. When on passing the gaseous product through aqueous sodium hydroxide, there's a further contraction of 30 cubic centimeters. What does this mean? Okay, yeah. And all volumes measured at RTP. Okay, so let us try to work through the problem using the blank space as well. So we'll use the same general formula. Okay, that is CXHY. Okay, which benefited us earlier. So okay, so we have CXHY gas plus X plus Y over 4 O2 gas, and we get X CO2 gas plus Y over 2 H2O liquids. Now I'm going to highlight in red here. Okay, this is liquids, so therefore it will not be involved when you write out all the volume ratio, because liquid being liquids is not involved in the measurements. Okay, so do take note of that. Okay, so if we move on, we will start off with 10 cubic centimeters of hydrocarbon. Okay, so let us try to keep the same way of working. So we have VI. Okay, so we will have V initial here in terms of cubic centimeters. That's 10. Oxygen, you will just hold excess. So this is open to interpretation. So what do we actually mean by excess? Okay, so well, you can just give it a variable. So you can call it A, for example. Okay, or some people like to write it as A plus A prime. Okay, so it's really up to you. Okay, so if you like it, you can write it as just A as a ballpark volume for excess. Okay, of course CO2 at the start is 0. Okay, so we'll keep to the same way of writing. So we're going to have the final volume over here, and you'll notice that there's a because it's excess, right? So you would expect complete combustion. So we have 0 here. And then we have some excess oxygen. So we just write it as A prime. Okay. And CO2, we don't know how much we have. Okay. We don't know how much. However, you can tell from the parts are highlighted in baby blue. When you pass the gaseous product through aqueous sodium hydroxide, there is a further contraction of 30 cubic centimeters. So this tells us that 30 cubic centimeters here is CO2 because this is the volume um, of acidic gas being absorbed by sodium hydroxide. Okay, so I hope this is clear enough to you. Okay, then the final column here will have the volume reactants. So reacting volume, okay, per cubic centimeters. So that will be 10. Okay, and then of course the reacting volume will be the difference, A minus A prime, and then produce 30. Okay, now we need to do some mathematics here. Okay, the mathematics we need to do is related to this portion highlighted in orange. You were told that after the reaction, there's a contraction of 20 cubic centimeters. Okay, so that means over here, right, we need to take the difference between the initial and the final volume. So when we say that there's a contraction of 20, right, that means that the final volume is 20 cubic centimeters less than the initial. Okay, does that make sense to you? Right, so in that case, can we say that the final volume is equals, sorry, the initial volume is equals to the final volume plus 20. Okay, so that means I will have 10 plus A, which is equals to A prime plus 30 plus 20. Okay, then after that, I'm going to shift the equation around. I'm going to get A minus A prime to be equals to 30 plus 20 minus 10. So that will be 40. Okay, so therefore A minus A prime is actually 40 cubic centimeters. And this is a very important conclusion we need to have. So this is actually 40 cubic centimeters. So from here, we know that it's 40 cubic centimeters. Okay, then we can have the mole ratio. So the reacting ratio. So that will be 1:4:3. Okay, will that be okay? Right. Yeah. So because this is already in unity, so we can conclude that x is equals to 3. Would that be okay? Right. So if x is equals to 3, then we can simply just solve it by simple mathematics. Yeah, because x plus y over 4 is equals to 4. So that means that I'm going to have 3 plus y over 4 equals to 4. Y over 4 equals to 1. So y is 4. Okay, so therefore I conclude that the molecular formula of my hydrocarbon is C3H4. Okay, which fits into everything, all the information. Okay, so if you face difficulty in working through this problem, you might want to spend a bit of time thinking about it and running it through again. Yeah, it's important that you are aware how to go about working with such problems in a fast way, especially like if you look at exercise 2.6. Yeah, sometimes you can get them in MCQ, and it could be a little bit daunting. okay, if you are not sure how to work through them. Right. Okay, so without further ado, we'll move on to exercise 2.6. We have question 1. So it's a multiple response kind of MCQ. So you are given 20 cubic centimeters of gaseous organic compound. You spark it with excess oxygen. So you have to read it carefully. Produces 20 cubic centimeters of CO2 and 80 cubic centimeters of water vapor. All gases measured at the same temperature and pressure. This is important because they are trying to tell you that mole ratio is the same as volume ratio. So which of the following molecular formula fits the data? Yeah. So this is important. Okay. So the first thing we need to do is can we convert them to a proper molecular formula, because these are what we call condensed structural formula. You learn them in organic chem eventually. So in that case, we have 1, 2, 3, 4. So we're going to have C4 H10. Okay, so this is a molecular formula. Then this will be 1, 2, 3, 4 C4 H5, 6, 7, 8 H8O. Okay, and third option would be C4 and then 3, 4, 5, 6, 7, 8 H8O2. Okay, so off the top of my head, if you simply look at a CXHY gaseous plus X plus Y over 4 O2 gaseous, you get XCO2 gaseous plus Y over 2 H2O. In this case, gaseous because I mentioned water vapor. Okay, excess oxygen. So you don't know how much oxygen, but you can straight away look at the reacting volume. Okay, so you notice that when you do MCQ, you can do it quite fast. So reacting volume with 20, react with a lot of oxygen. It gives you 80 cubic centimeters of this and 80 cubic centimeters of H2O. So the simplest ratio will be 1:4:4. Okay, so therefore from here, right, X to Y over 2 is 1:1 ratio. Yeah, so I mean to be specific, it should be 4:4. So in this case, Y will be 8. Yeah, so we need to look at C to H, right? Ideally 4 to 8. Yeah, so in short, option 2 and 3 will be correct. Option 1 is incorrect. Okay, so this is how we can work on it quite quickly. Yeah, especially for MCQ, you really don't have a lot of time to think through a lot of stuff. I mean, it's not incorrect not to think through a lot of stuff, but rather sometimes you have to be a little bit more strategic when you are working through MCQs. Okay, then next, let us look at question 2. You were asked what volume of oxygen is required for the complete combustion of a mixture containing 5 cubic centimeters of methane and 10 cubic centimeters of ethene. Okay, so the simplest way again is to write out balance equations. Yeah, so you have CH4. I'm not going to write out the state symbols. Okay, so plus O2 here. So complete combustion. So I'm going to get CO2 plus 2H2O. So we're going to need 2 equivalent of oxygen, and then ethene will be C2H4. Okay, again plus O2. I'm going to get 2 CO2 plus 2H2O. So again, total amount of oxygen will be 3. Okay, so the stoichiometric ratio is 1:2 for methane and 1:3 for ethene. So that means that if I have 5 cubic centimeters of methane, I'm going to end up, or rather I will need at least 10 cubic centimeters of O2 for complete combustion. If I have 10 cubic centimeters of ethene, I will need 30 cubic centimeters of O2 for complete combustion. Yeah, so therefore, the total volume of oxygen required would be the summation of 10 and 30. So that will be 40 cubic centimeters. Okay. Next, we move on to question 3. So over here we have 20 cubic centimeters of gaseous hydrocarbon Y exploded with 100 150 cubic centimeters of oxygen. So the residual gas occupies 130 cubic centimeters. So again, this is another interesting question. So there's residual gas. Residual gas occupies 130. And then the next portion, of course, is really important. After shaking with excess sodium hydroxide, final volume is 90. Okay, so there's a reduction. So if you are sharp enough, you will realize that if the residual gas occupies 130 and after shaking final volume is 90, so therefore the difference will be the volume of CO2 evolved. Okay, so if you could do that, then that will be excellent. Okay, so very quickly we can work using the same formula as well. You were told the volume all measured at room temperature conditions, so therefore water will exist as liquid. So CXHY gas plus X plus Y over 4 O2 gas. Okay, so you will get XCO2 gas plus Y over 2 H2O liquids. Okay, so we'll fill in the information here. So we have initial volume in terms of cubic centimeters. So that will be 20 and 150. Then I'm going to have 0 and dashed. And then the final volume, because you assume that 150 cubic centimeters of oxygen is in excess, so I'm going to have 0 here. Okay, then I wouldn't know how much oxygen remains. Okay, but let's just call it A, for example. So we have A here, and then earlier on, if we take the difference between 130 and 90, we're going to get 40 cubic centimeters of CO2. Okay, so I think we are quite clear over here what's going on, right? And one more piece of information we need will be the reacting volume. Okay, so in this case, reacting volume in terms of cubic centimeters, that will be 20. Okay, so what's the volume of oxygen gas reacted? We don't know, so we just put it as 150 minus A, and then and this actually produces 40 cubic centimeters of CO2. Okay, yeah. Then in order to find out what A is, since we were told that the residual gas occupies 130 cubic centimeters, then we need to find out what constitutes the residual gas. So based on the final volume, that would be the excess oxygen and CO2 over here. So that means that I can equate A plus 40 to 130. So A will be equals to 90 cubic centimeters. Okay, then from here we will be able to find out what is the reacting volume of oxygen. So that will be 150 minus 90. So that will give us 60 cubic centimeters. We're just going to erase this. Okay, so this would give us 60 cubic centimeters. Okay, so therefore the simplest ratio will be 1 is to 3 is to 2. Okay, so if we get 1 is to 3 is to 2, the next thing we're going to do is we are going to equate. So x is equals to 2 and x plus y over 4 is equals to 3. So that will be 2 plus y over 4 equals to 3. So therefore y is equals to 4. Okay, so the molecular formula of y would be C2H4. Okay, so that's how we work through the problems and get the molecular formula of y. Okay, next question 4. Okay, so for question 4, you are given 20 cubic centimeters of gaseous hydrocarbon. Again, you mix it with 150 cubic centimeters of oxygen. Okay, so that the hydrocarbon was completely burned, and then volume of gas remaining at the end of combustion was 100. Okay, so after passing, so again, these are some important data. Volume of gas at the end of the combustion was 100. Then after you pass it through potassium hydroxide, the volume was reduced to 20. So from here, you can tell that the volume of gas absorbed is actually 80 cubic centimeters. So that would be CO2. Yeah. So with that, then I guess we can use the same table. So we're going to use the same table over here. Okay, so that we don't have to rewrite it. Okay, so we start with 20, and then again we have 150 cubic centimeters of oxygen, and then CO2 will be 0 and then dashed. Okay, the gas measured at 20 cubic centimeters, so this is liquid, so this is correct. Final volume, you wouldn't expect any hydrocarbon. Okay, then again, you don't know the volume of oxygen, so you just let it be A. Okay, you know the volume of CO2, so that's 80. Okay, so the reacting volume again is 20, 150 minus A, and then 80 over here. Okay, then there is one piece of data that is important. Volume of gas remaining at the end of the combustion is 100 cubic centimeters. So that means that we will equate A plus 80 to 100. So therefore A is equals to 20 cubic centimeters. Yep, so that means that the volume of oxygen reacted with the hydrocarbon would be 150 minus 20, so that will be 130 cubic centimeters. Okay, so if we take the simplest ratio, okay, so that would be 1 is to 130 divided by 20, so that is 6.5 is to 4. So 1 is to 6.5 is to 4. So therefore, from here, you can tell that x is equals to 4. Okay, and 4 plus y over 4 is equals to 6.5. So therefore, y is equals to 2.5 times 4, that's 10. Okay, so the formula of the hydrocarbon is C4H10. Okay, so the method of doing is quite similar, but they require a very strong logical sense. Yeah, so I think it's something which comes quite naturally with practice, but at the same time, if you think through the problem, it should be okay. Okay, yeah. Then 2.6, we have calculations using concentrations. So you were told that when a solute is dissolved in a solvent, solution is water, I think you know this, solvent is water, aqueous solution. So you need to know what is aqueous solution. So aqueous solution simply means that the solute dissolved in water. Okay, if the solute is dissolved in a solvent other than water, you just call it a solution. Okay, then yeah, I think concentration, all these terms is something which you are familiar with, so I don't think I need to go into details. Okay, and you would be able to understand what exactly we meant by dilution. Okay, so basically you add more solvents to the concentrated solution. Okay, so the amount of the solutes remain unchanged. No need to memorize, but that's something logical if you think about it. Okay, so you just imagine that you have a concentrate, you have orange or lemonade concentrate. Yeah, so if you just take out 10 cubic centimeters into a huge jar and then you fill it with water, despite having a much bigger volume, the amount of concentrates remain the same. So that's what it means. Okay, so if you have exercise 2.7, we have 14.3 grams of hydrated sodium carbonate. You dissolve it in water. Remember that if they give you the hydrated version, if you calculate the relative molecular mass, you have to include the water of crystallization. Of course, here the MR is given to you, so in that sense, you are quite lucky because they gave you the MR. But in the event that the MR is not given, you have to include the water crystallization here. Okay, You dissolve them in water, and then the solution make up to 500 cubic centimeters in the volumetric flask. And then what is the concentration of sodium ions? Okay, so first of all, it will help if you can calculate the number of moles, the amount dissolved of sodium plus. I think we can get to the root of the problem straight away. So basically, that will be the amount of hydrated sodium carbonate, 14.3, divided by the relative molecular mass, that's 286.0. Okay, and because one equivalent of sodium carbonate hydrated gives you two equivalent of sodium plus, so you need to multiply this value by 2. Okay, so from here you get 0.10 moles. Okay, because you made up to 500 cubic centimeters, so therefore the concentration of sodium plus is equals to 0.10 divided by 0.500, so that will be 0.200 moles per dm cube. Okay, remember to always write your units. This is especially so for practicals. Okay. Okay, next we have exercise 2.8. Question 1 asks to calculate the volume in cubic centimeters of a solution required to provide 0.85 grams of ethanoic acid from a 0.30 moles per dm cube solution. Okay, I think the simplest way again is to convert the mass to amounts. So from here, we can easily work out the amount of ethanoic acids. Okay, so that would be 0.85 divided by 60. So if you punch your calculator, you should be able to get 0.01417 moles. Okay, yep. And so from here, you are asked to calculate the volume you need, okay, from this concentrated solution. Okay, so what you can do is simply the volume required, okay, is simply equals to the amount divided by the concentration. Okay, so you're going to end up with 0.0472 dm cube. Yeah, so you always be good to convert to cubic centimeters, so that will be 47.2 cubic centimeters. If you are not sure whether you should divide or multiply, I suggest that you think it through using some fundamental knowledge. Okay, so for example, right, you know that the concentration of ethanoic acid given to us is 0.30 moles in 1 dm cube. So that is 1.00 dm cube. Okay, so this is the concentration. Okay, right. Now, in this particular question, I want to find out the volume I need to give me 0.85 grams. Essentially, it's 0.01417 moles. Okay, so in order to get the volume term to the top, right? So it does make sense that from here, if the amounts I have is 0.0147 in terms of moles, okay, I would need to divide it by the concentration term, because if I divide it by the concentration term, then I will be able to bring the volume up. Yeah, so this essentially is equals to 0.01417 moles multiplied by 1.0 dm cube divided by 0.30 mole. So you cancel off this, and then eventually you get the answer in terms of dm cube. Yeah, so if you can go back to the fundamentals and think it through this way, I think it's a lot easier rather than just memorizing whether you should divide or multiply. So I hope that helps you to clarify some of the difficulty which you might encounter when you were in secondary school. Okay, for question 2, you have a agricultural biochemist use this particular compound, 6-benzyl aminopurine in trace amount as a plant growth regulator. So the typical application, 150 cubic centimeters of a solution contains 0.030 milligrams of the compound. So again, we need to convert the mass. So it's quite standard. We always convert mass to amounts, because working with amounts is the fundamental way of working through stoichiometric problems. So again, therefore the amount of the compound, okay, is equals to 0.030 multiplied by 10 to the power of minus 3. You'll notice that when I work through the problems, right, I always like to place the power term in this format. I will not want to write them out as a string of numbers. This allows me to track the power terms in an easier manner, and it will avoid or prevent myself from making mistakes. Yeah, so this is just a personal preference. You can follow if you wish to. And then divide by the relative molecular mass. So again, you can punch your calculator to calculate the relative molecular mass of 6-benzyl aminopurine. Yeah, so you would end up with 225.0. Okay, so from here you will get 1.33 times 10 to the power of minus 9 moles. Okay, always write in standard forms. It's easier to track. Remember this. Okay, so the power term is the power minus. So do take note of that. And so concentration. So we have 150 cubic centimeters. So therefore, the concentration of the compound, which is 6-benzyl aminopurine. So I'll just write it as concentration of compound is equals to 1.33 to the power minus 9 divided by 0.150. Okay, so this will give us 8.89 times 10 to the power minus 7 moles per dm cube. For most calculation concentration kind of question, the concentration is always, almost always in moles per dm cube. Just take note of that. Okay, so for question 3, you have a sample of concentrated nitric acid with a density of 1.41 grams per cubic centimeters. It contains 70% of nitric acid by mass. Yeah, so this is a typical kind of problems you get when you want to prepare solutions and they do not give you the concentration in terms of moles per cube. So they give a density and they give you the percentage by mass. Yeah, so this is usually a little bit challenging for students, but you just need to work through the logic and you will see that it's not that difficult. Okay, yeah. So the first thing you might want to do, right, because you were told that 70% by mass of nitric acid is actually contained in the solution. Yeah, so you need to convert or scale it. So therefore, the concentration of nitric acid, okay, is equals to 0.70 multiplied by 1.41. Okay, divides, because we need to convert to moles per dm cube. So nitric acid is 1 plus 14 plus 48. So that will be 63. So divide by 63.0. Okay, this is in terms of moles per cubic centimeters. Okay, so if you do a quick calculation, let me just punch the calculator to see what is the answer which I will get. So 0.7 times 1.41, yeah, divide by 63. So I'm going to end up with 0.0157 moles per cubic centimeters, but I can't leave concentration in moles per cubic centimeters. I need to scale it up to moles per dm cube. So again, to scale it up, 1, 2, 3. So this is equals to 15.7 moles per dm cube. Okay, we'll move on to the next part, which is exercise 2.9. So first question, calculate the volume of 18.0 moles per dm cube of sulfuric acid that's required to prepare 2 dm cube of a diluted solution of sulfuric acid, which is 0.3 moles per dm cube. Okay, I think the easiest way, there are a lot of ways to do it, but I feel that the easiest way is simply to find out the number of moles this contains. Because the number of moles this contain will be the amounts you need to abstract, or rather the volume you need to abstract from 18.0. Okay, so we can easily determine the amount of H2SO4 I need over here. So that will be 0.300 multiplied by 2. So that will be 0.600 moles per dm cube. Sorry, moles, in terms of the moles. Okay, then after that, what I'll do is how much do I need to abstract from here? So remember earlier on the logic which I brought you through over here. Yeah, so you can work it through using using similar logic. Yep. Okay, so from here, what I'll do is, so volume required, volume of H2SO4 required is equals to 0.600 divided by 18.0. So I'm going to end up with 0.0333 dm cube. So I need to convert it to cubic centimeters, so that will be 3.3 cubic centimeters. Yeah, so remember that when you do dilution, you add the concentrated acid to water, not the other way around. So you might want to ask why, or think about why is that the case. Question 2, what would be the concentration of the final mixture made by 385 cubic centimeters or 0.725 moles per dm cube of HCl and 525 cubic centimeters or 0.325 moles per dm cube of HCl? Yeah, it seems quite confusing, right? But it's okay. We just need to know two things. First, total number of moles of HCl. Okay, so that will be 0.385 multiplied by 0.725 plus 0.525 multiplied by 0.325. Okay, so this will be the total amount of HCl. So if you do a quick punching on the calculators, you should get 0.4498 moles. Okay, then after that we need the total volume. So V total. So that would be 0.385 plus 0.525. So I'm going to get 0.9910 cubic centimeters. Yeah, so concentration of HCl would then be 0.4498 divided by 0.910. So that would be 0.494 moles per dm cube. Okay, pretty straightforward calculation if you ask me. Right. Okay, so without further ado, we'll move on to exercise 2.10. Okay, question 1, what is the volume of 0.05 moles per dm cube of potassium dichromate solution required to produce this? So again, it's the similar kind of problems involving dilution. So we'll work through the same method. Okay, so again, 500 cubic centimeters of 0.02 moles per dm cube. So therefore, the amount of dichromate would be 0.0100. Okay, so just half times this. Okay, then the volume required. So volume required, which is based on this concentration, would then be oh, sorry, I think I wrote the wrong units here. So this is 0.0100 moles. So the volume required will be 0.0100 divided by this concentration, which is 0.0500. Okay, so I'll end up with 0.2 dm cube, which is 200 cubic centimeters. So it's kind of like a repeat of what we do earlier on. What we did earlier on, that means. Okay, question 2. Calculate the concentration of sodium plus in a solution made by mixing 3.58 cubic centimeters of this concentration of sodium chloride. Okay, with this concentration, this volume of sodium sulfate. Yep. So again, we need to be aware of the total volume. Okay, so and of course not only the total volume but also the total amount of sodium plus. Okay, so the total amount of sodium plus, because we are supposed to determine the concentration of Na plus in a solution. So amount of Na plus is equals to 0.00358 times 0.288 plus 0.500 multiplied by 6.51 10 to the power minus 3 multiplied by 2. You might be wondering why multiply by 2. Yeah, because it's sodium sulfate, which is Na2SO4. Okay, so the multiplication by 2 is important. So eventually we'll end up with the amount of sodium plus ions is 7.531 times 10 to the power minus 3 moles. Okay, then what about the total volume over here? Yeah, okay, so the total volume is 3.58 plus 500. So therefore the concentration of Na plus is equals to 7.531 times 10 to the power minus 3 divided by 0.50358. Okay, so this would be equals to 1.50 10 to the power minus 3 moles per day cube. Okay, it's a similar calculation we did earlier on. Okay, so finally, question 3. You will ask, what is the volume of water that must be added to this volume of this concentration of sodium hydroxide to obtain a new concentration of 0.01 moles per dm cube. Okay, so again, when we work through the problem, the first thing we might want to ask ourselves is what is the amount of sodium hydroxide present? So the amount of NaOH is 0.150 multiplied by 0.0262, which is equal to 0.00. Maybe we write it in standard forms. Okay, so that would be 3.93 times 10 to the power minus 3 moles. Okay, then so therefore the total volume I need in order to create this particular concentration. So the volume I will need for this particular concentration is equals to 3.93 10 to the power minus 3 divided by 0.0100. So the total volume, so the actual volume is 393 cubic centimeters. Yeah, so initially I have 150, but the volume I will need in order for the concentration to be 0.0100 is 393. So therefore the volume of water I need to add is the difference between the two. So 393 minus 150. So that will be 243 cubic centimeters. Okay, the next portion here is actually planning. Yeah, so basically you will encounter some of these things in the laboratory. So like generic procedure for preparing a solution from a solid. So usually you will need an electronic weighing balance. Usually the precision is to the second decimal place, but I think some schools have it third decimal place. Okay, so weigh accurately about a certain mass of solids, and then normally you will transfer it into a beaker first, not conical flask, because conical flask difficult to stir. So you transfer it into a beaker, so you dissolve in deionized water or any solvent which you require it to dissolve in. Okay, usually you will reweigh the weighing bottle, take the difference to find out the amounts transferred. If you don't want to do that, you can always rinse your weighing bottle with the required solvents, and then you transfer everything in. So therefore, the amounts you weigh will be the amount transferred. Yeah, so depends on what you think is convenient for you. Yeah, and then after that, you through a funnel, right? So usually you will put a funnel here, and then you will pour it in to a 250 cubic centimeters volumetric flask. It need not be 250, it could be 100, it could be 150, it could be 15, depends on your needs. Like usually the standard ones given in the school lab is 250, and then you top up to the required volume, okay, with deionized water. And then normally you stopper it and then you swirl, or you can say shake well to obtain a homogeneous mixture. Yeah, this is a very important table you need to be familiar with in order for you to record your data. Okay, whether is it in planning or in an actual practical experiment. Yeah, so you need the mass of empty weighing bottle, the mass of weighing bottle and solids. And then if you reweigh, you'll be the mass of weighing bottle and residual solid, and then the mass of solid used. Yeah, if you actually rinse the contents of the weighing bottle, meaning you try to rinse the residual solid into the volumetric flask, then you do not need this row. Okay, but you need to indicate it somewhere below to indicate that you have actually rinsed the contents of the residual solid into the volumetric flask, that is. Yeah. The next section we're going to go through is on planning to prepare a series of solutions of different concentrations. Yeah. So normally the solutions which you have at the beginning is what we call a stock solution, and it is usually quite concentrated. Yeah. So it is the kind of skills which you need to have in your titration, where you are given a bulk solution and let's say of a known concentration, say 2 moles per dm cube, and then they will ask you to pipette out 25 or 10 cubic centimeters, and then you release the solution from the pipettes directly into the volumetric flask, and then you top up to the mark with deionized water. Yeah. So normally you ask to do that for titration, and that is for you to prepare a more diluted solution in order to use that for titration. Yeah, sometimes you do that not just once but a few times to prepare a series of solutions of different concentration from one single bulk solution. So for example, in these examples we have sulfuric acid. The concentration is given to be 2 moles per dm cube. Yeah, and then we are asked to prepare a diluted version 0.50, 1.00 and 1.50. Yeah, so from here there are several ways you could do that. You could either do that in 100 cubic centimeters volumetric flask, and then you use pipettes to pipette out 25.00, or you can use a burette, up to you, and then you release it into the volumetric flask, and then you top up to remaining 75 cubic centimeters with deionized water, and then you repeat it for 50 cubic centimeters, again either pipette or release from a burette, and then 75.00 cubic centimeters to prepare the diluted solution of 1.50 moles per dm cube. Yeah, the calculation wise, you have gone through that earlier on in our examples, so I don't think that is a major issue. And then the generic procedure for writing up is given here, so I don't think it's going to pose any difficulty. Sometimes we need to prepare a very diluted solution. So for example, 0.010 moles per dm cube from a very concentrated solution. Yeah, so you might be thinking that, okay, I can simply just use a micro pipette to take out a small bit, so let's say 0.5 cubic centimeters, and then I just top that with deionized water to 100 cubic centimeters mark. This you might seem easy. However, sometimes, or rather in most cases, it's difficult to measure out 0.5 cubic centimeters with a high precision. So you tend to encounter a large measurement error. So normally what we do is we'll go through what we call a serial dilution. Yeah. So for example, in our case here, we will first prepare a solution of 1.00 moles per dm cube. So what we do here is perhaps using a 50 cubic centimeters pipette, I will release the solution into a 100 cubic centimeters volumetric flask, and then I top it up with deionized water, and then I swirl to ensure even mixing, and then I will label this as solution 2, where its concentration is 1.00 moles per dm cube. After that, I will use a pipette to pipette out 10 cubic centimeters. I will release the 10.0 cubic centimeters into another 100 cubic centimeters volumetric flask, and then top it up with deionized water, so to ensure even mixing, label as solution 3, and then I do the same thing. I pipette out 10.0 cubic centimeters, release it into a new 100 cubic centimeters volumetric flask, top it up with deionized water to the 100 cubic centimeters mark, and then after that, so to ensure even mixing, label this as solution 4, and then this is how I get 100 cubic centimeters of, let's say, a very diluted solution. Yeah, so this method is known as zero dilution, so it's something for you to take note of as well. Yeah, to ensure that the bulk sample which you retrieve, ensure that it is a certain volume where you can measure with certain accuracy. Okay, we will move on to section 3 on acid-base reactions, which most of you should be extremely familiar with from secondary school. Yeah, so you know that acid and bases importance in many chemical process. Back in secondary school, most of you understand the definition of acid and bases through a very ancient concept, what we call Arrhenius Theory of acids and bases. So what do we mean by that? Yeah, most of us know acid as a species which produces H plus or H3O plus. Okay, H plus doesn't exist on its own because it's very unstable. So normally the represented form which we write on paper is H3O plus, but it is perfectly fine to write it as H plus as well for simplicity. Okay, so normally we use these two interchangeably for solvated H plus. Yeah, so this is what we define as an Arrhenius acid. For an Arrhenius base is a substance which ionizes in water to give OH minus. So that means it produces OH minus. Typically, sodium hydroxide, potassium hydroxide. Yeah, that is something you are extremely familiar with. Yeah, then the all-time favorite, maybe not favorite, but familiar reactions involving hydrochloric acid and sodium hydroxide to produce salt and water. So this is a typical example of Arrhenius acid-base reaction. Okay, normally we'll write it as an ionic reaction form, just to showcase what exactly is happening. Yeah, so when we have H plus and we have OH minus, okay, this lone pair of electrons will donate its electron density to the H plus, and in the process it forms a new HO covalent bond. Okay, yeah. So this new HO covalent bonds, later on in energetics you will learn, it releases heat. Yeah, so and then it will heat up the solutions. So the acid-base reaction, if you are sharp enough, you touch the base of your conical flask, it tends to be quite warm. Okay, yeah. So there is a limitation to this particular theory because it's only applicable to aqueous solution, and it is a very narrow definition of a base. So later on, two famous scientists, Bronsted-Lowry, came up with a new theory known as Bronsted-Lowry acid-base theory. Okay, and you notice that it is quite similar to Arrhenius, but there is a slight difference. Okay, so in this case, an acid is a proton donor, so it donates a H plus. You notice that these words are bolded, so it's important. So a Bronsted acid donates a proton or H plus. A Bronsted base accepts a proton, okay, or H plus. So the definition is pretty narrow here. Proton donor, proton acceptor for a Bronsted-Lowry base. Yeah, so be very clear about that. So the difference is that unlike Arrhenius base, a Bronsted base need not be hydroxide only. So a lot of species could be a Bronsted-Lowry base. So for example, ammonia or molecular ammonia. So you know that molecular ammonia, it accepts a proton from an acid, so to give you the corresponding ammonium. Yeah, so ammonia is considered a Bronsted-Lowry base. You can either call it a Bronsted base or Bronsted-Lowry base, doesn't really matter. Okay, but there is still a limitation to this particular theory because it is still restricted to aqueous chemistry largely. Yeah, and the acids definition still focus on the fact that it releases a H plus or it donates a H plus. It doesn't. It's not general enough. Yeah, and for a base, it must accept a H plus. So that means that the drawback of Bronsted-Lowry acid-base theory is that the whole definitions or the whole idea focuses around proton transfer, which a lot of reactions might not involve proton transfer. Yeah, so in the late 19th century, Lewis came up with a new definition. So he defines an acid, a Lewis acid in that case, as an electron pair acceptor and a Lewis base as an electron pair donor. So in that case, if you look at the reaction between BF3 and ammonia, you'll notice that both of them do not exchange protons. So what exactly happened is that the lone pair on ammonia donates to the boron center. Yeah, so I'm drawing this purple arrow. Later on in organic chemistry, you will learn this. You will understand this notation. So that means that the lone pair of electrons is being donated to the boron center. Yeah, so we call the ammonia center the Lewis basic center, delta minus, delta plus. We call the boron center the Lewis acidic center. So please learn how to use these terms: Lewis basic center and Lewis acidic center. Yeah, so ammonia being a proton, sorry, being an electron pair donor, so it's called a Lewis base. BF3 being an electron pair acceptor is called a Lewis acid. So after the reaction, you form an adduct. So this is known as adducts. Some of you might be asking, so does it mean that the usual H plus over here and OH minus, is it still considered a Lewis acid base reaction? Yes. You can view a proton as an electron pair acceptor. So the proton accepts an electron pair for OH minus. So in the process, you form a new covalent bond. So yes, H plus is an electron pair acceptor, so it's Lewis acid. OH minus is electron pair donor, so it's a Lewis base. Okay, so therefore, something that is a Lewis acid or Lewis base need not be a Bronsted acid or Bronsted base. Yeah, but a substance or a pair of substance that are Lewis acid, sorry, they are Bronsted acid and Bronsted base, they are necessarily Lewis acid and Lewis bases. Okay, just make sure you know what's going on. Okay, yeah. There's a limitation to Lewis acid-base theory. The limitation is that it is too general, so too generic. So sometimes it's difficult to apply. Yeah, but I think to understand reaction, it is of utmost importance for you to be familiar with all these two models, especially Lewis acid-base model. Arrhenius is too ancient, so I mean, it's good to know that it exists, but it has limited application in the world today. We'll move on to exercise 3.1, okay, where we are supposed to identify the Bronsted acid and base in the following forward reaction. Yeah, so that is probably not too difficult. Okay, so in the case of so I will just represent acid as A and base as B. Okay, yeah. So Bronsted acid base theory. Let us recall proton, donor, and acceptor respectively. Okay, so you'll notice that nitric acid donates a proton to ammonia, forms nitrate and ammonium. So therefore, nitric acid is a Bronsted acid, ammonia is a Bronsted base. Okay, then H2O and nitric acid. So in this case, nitric acid again is a Bronsted acid, and water is a Bronsted base. Yeah. HCl and ammonia. So in this case, ammonia is a Bronsted base because it accepts a proton from HCl. So this is acid. Yeah, H2SO4 liquids and HNO3. So we have to be a bit careful here. We need to check out which one accepts the proton and which one donates the proton. So you notice that H2SO4 is the one that donates the proton. So therefore, sulfuric acid or concentrated sulfuric acid is the Bronsted acid, and concentrated nitric acid is the Bronsted base. Okay, it might be interesting for you to note that for the forward reaction, it generates, like let's say nitric acid is the acid, so it generates nitrates. Yeah. Later on in acid-base equilibrium, you will call nitrate the conjugate base, and you will call ammonium the conjugate acid. Yeah. So we call nitric acid and nitrates a conjugate, an acid conjugate base pair. Yeah. So you notice that when an acid donates a proton, it becomes a base. So when a proton accepts a H plus, it becomes an acid. Okay, but we normally don't call it becomes an acid. We call it becomes a conjugate acid, just to differentiate between the two. Yeah, but you will learn more about that in acid-base equilibrium. So not to worry too much. Okay, yeah, and then over here we talk about the three models of acid-base theory. So they are being used to interpret the different acid-base systems. Yeah, so normally for Arrhenius, I think it works very well when we have water. So for Bronsted-Lowry theory, for example, in the case of HCl and ammonia, without water, we can still discuss the chemistry. Okay, then for corn nitric acid and corn sulfuric acid as well. Yeah, anything beyond proton transfer, I think Lewis acid-base theory works better. Yeah, but just to take note that you are going to learn quite a bit of this in a chapter later on, especially in GC2. It's what we call acid-base equilibrium. So this particular chapter, usually your seniors find it quite difficult. So just be prepared for it. So I think before you get yourself prepared, make sure that you learn chemical equilibrium well. Okay, yeah. 3.2, we are going to talk about titration, which is something you are extremely familiar with from secondary school. So I don't think I need to go into details of what exactly is titration, but there are some terms which you need to know. Okay, especially so in practicals. So for example, the first term you need to be familiar with is what I call a standard solution. A standard solution normally is a solution with a known concentration. Yeah. So and then as you perform your titration, there will be a point where it's almost the exact volume, where you need to introduce in order to react away one component entirely. So for example, if I pipette out 25 cubic centimeters of HCl into the conical flask, then you release sodium hydroxide from the burette. So there will be a volume where all the HCl will react completely. So that is known as the equivalence point. Yeah. Later on, you will learn something called the endpoint, which is a little bit different. Okay, over here. So we actually have the terms here. So this is the endpoint. So there is a slight difference between equivalence point and endpoint. Okay, usually you obtain endpoint with the help of an indicator. Yeah, so an endpoint is normally obtained through an experiment. Yeah, so sometimes because of the limitation of the instrument, the amounts you are going to add will either exceed a bit or it will be slightly below the just nice portion. So let's say you need exactly say 25.03 cubic centimeters, but you know that from the burette you can't introduce this volume. Yeah, but still you will stop your titration because the endpoint color has changed. Yeah, so we call that endpoint. The equivalence point, you can call it a theoretical endpoint if you want to, but we try to differentiate between the two. Okay, yeah, so the volume which you have added and it reaches the endpoint, right? This is what we call the tidal volume. Yeah, I think that's quite standard, which something you have learned from secondary school. Later on, you'll learn more about this from acid-base equilibrium, but when you are performing your titration, you need to use indicator, and this is especially the case for acid-base titration. So indicator has what we call as a working range. So again, you will learn more in acid-base equilibrium. So there are several indicators which are common, and they will come out in your exams. And you will tend to use bromomethyl blue and dimer blue in your acid-base titration. The rest is not being recommended because they found that it was found that they have some carcinogenic properties. So we try to avoid letting students use them. Yeah, so bromothymol blue and dimer blue are quite common. So just ensure that you know how to differentiate their color. Okay, so for example, when you're introducing sodium hydroxide into HCl, because this is what we call the endpoint. So for the endpoint, right, the pH will change quite drastically from, let's say, around 3-ish to about 12. Yeah, so in that case, because the pH changed quite drastically, any indicator with a working range within this region should work quite well. Yeah, okay, so let's say for phenolphthalein, the color change will be from colorless to pink. Then from methyl orange, you'll be from red to orange. Okay, yeah. And then for planning, this is the generic procedure for writing titrations. So make sure that you are familiar with it. Especially, these are some of the points where your seniors tend to miss out, especially things like after you fill up the burettes, you'll be good to record the initial burettes reading. After your titration, you'll be good to indicate recording of the final burettes reading, and then make sure that you repeat the titration until two consistent titer of 0.10 cubic centimeters apart. This might be a bit different from what you learn in secondary school. Okay, the two titer values must be within plus minus 0.10 cubic centimeters before you stop your titration. Okay, this is a standard table which you need to write them out. Remember that whatever you record from the reading of the burettes is called a burette reading. It is not a burette volume. Okay, because you can only obtain the volume by taking the difference between the two readings. Okay, the reason being the volume which you read off here. So let's say this is 50, let's say, and this is 40, and it's 30, 20. Let's say you read off as 20, right? This is not really 20 cubic centimeters because the volume over here is not being accounted for. Okay, yeah, so just make sure that let's say your initial burette reading is 20, your final burette reading is 40, the difference is 20.00 cubic centimeters. Yeah, so just ensure that you are familiar with the writing of some of these terms. Don't anyhow write, okay? So burette reading, yeah, not volume, okay? Okay, next, yeah, something for you to take note of. There's also iodometric titration, which we will introduce to you all later on, because this is part of redox titration. Yeah, for iodometric titration, just to take note that the indicator you are adding is starch. Yeah, and you need to add at least 1 cubic centimeters of starch. Yeah, 1 or 2 drops is not sufficient to give you the intense dark blue color. Okay, for other indicators, usually it's just 2 to 3 drops as indicated here. Okay, yeah. So just make sure that you are also familiar with the types of titration. Iodometric titration, which involve iodine and thiosulfate, is very popular in H2 chemistry, especially so not in the titration form, but in kinetics later on you're going to learn in what we call the iodine clock reaction. Okay, redox titration, you do not need indicator because the cations, the metal cations themselves already has colors. Okay, and then acid-base titration is the one where you need indicator because usually the solutions are colorless. Yeah. Okay, so these are some things which you can go through on your own. Okay, then we have an exercise 3.2 and 3.3. So for 3.2, The student was given solutions of HCl and sodium hydroxide of unknown concentration. So he carried out titration and found that I need 27.50 cubic centimeters of solution, sodium hydroxide solution, to completely react with the 100 cubic centimeters of HCl. Okay, and then in a separate experiment, he used 18.40 cubic centimeters of sodium hydroxide to titrate completely 50 cubic centimeters of a certain fixed concentration of sulfuric acid. Okay, so the question asks, so what are the concentration of the given HCl and sodium hydroxide? Okay, I hope this calculation isn't too tough. Basically, what you need to do is work with what you know first. Okay, so I think we can use the information given for sodium hydroxide and sulfuric acid. We can write a balanced equation involving sodium hydroxide and sulfuric acid. So sulfuric acid H2SO4 plus sodium hydroxide 2 equivalent sodium hydroxide. In the course of the reaction, you get sodium sulfates plus 2H2O. Okay, so they react in a 1:2 ratio. Yeah, so from this information, you can easily calculate the amount of H plus present. Okay, you can do that by simply taking the concentration, which is 0.0782, multiplied by 50.00. So in this case, we write the in form 0.050 and multiply by 2, because one equivalent of sulfuric acid give us 2 equivalent of H plus. And then the final value I'm going to get is 7.82 times 10 to the power of minus 3 moles. So this is the amount of H plus present. This amount of H plus present is also the same as the amount of OH minus present in 18.40 cubic centimeters. Yeah, so simply by basing on this data, I can easily calculate the concentration of sodium hydroxide. Yeah, so from here I can easily determine the concentration of sodium hydroxide. It would be 7.82 times 10 to the power of minus 3 divided by 0.0184. Okay, so from here I will get 0.425 moles per dm cube. Okay, then based on this, I will use the first set of data to help me determine the concentration of HCl. Okay, so I can easily do that. What I will do is, actually I can just calculate straight away. The concentration of HCl is simply the amount which reacted with 27.50 cubic centimeters of sodium hydroxide. Okay, I will just take this volume multiplied by the concentration, which is 0.425. Okay, and then I will divide by the volume of HCl present, which is 100. So I will convert it to dm cube. Okay, and then yeah, with that I will be able to get my answer. So concentration of HCl will be 0.117 moles per dm cube. Okay, then moving on to exercise 3.3. So again, here we need to look at the data given to us. So we have 27.82 cubic centimeters hydrated sodium carbonate with this formula dissolved in water made up to 1 dm cube solutions. And then 25 cubic centimeters was neutralized by this amount of HCl. Yeah, so this is an acid carbonate reaction. Some of you might not be aware that carbonate is actually a base. Yeah, so sometimes in secondary school this was not told to us. Yeah, usually in secondary school, bases tends to be defined solely based on whether it can give OH minus. Yeah, so carbonate indeed itself is a base. Okay, so this is an acid carbonate reaction. So first we need to write a balanced equation. So sodium carbonate. Actually, you can write the ionic equation. It might be better in this case. So basically, carbonates plus H plus, and then I'm going to get H2O and CO. You might be interested to know that carbonate actually grabs these two H plus, right? And the first product is going to form is what we call carbonic acid, H2CO3. But this is not stable. Yeah, so because it's not stable under normal condition in aqueous medium, it will straight away decompose to give you H2O and CO2. Yeah, so that's something you might want to be aware of. Yeah, so from here we can quickly determine the amount of H plus present. So the amount of H plus is simply 0.10050.0488. Okay, so I will be able to get 4.88 times 10 to the power minus 4 moles. Yeah, and because carbonate to H plus is in a 1:2 ratio, so I just divide by 2. Then I will be able to get the amount of carbonates. Let's divide by 2, I will get 2.44 and the power minus 3 moles. Sorry, I think I wrote wrongly. It should be minus 3, not minus 4. Okay. Yep. Then remember that this, let me just highlight, this amount is present in 25 cubic centimeters. Okay, so it's present in 25 cubic centimeters. We need to scale it up to 1 dm cube over here. So we need to scale it up to 1 dm cube. Yeah, so from here, we need to calculate the concentration of carbonates in 1 dm. Okay, maybe not concentration. I mean, we can calculate concentration, but in this case, I think it's easier to just say the amount of carbonate present in 1 dm cube. So amount of carbonate present in 1 dm cube. Yeah, so it's simply 2.3. So we scale it. So scale it by dividing by 25, multiply by 1000. Okay, so with that, I will get 0.0976 moles. Okay, then I think from here is stoichiometry. Yeah, because you notice that this amounts would actually come from 27.82 grams of hydrated sodium carbonate. Okay, so what I can do is I'm just going to erase this portion so that there's some space for me to continue writing. Okay. Okay, so I'm just going to take 27.82 divide by the MR. So the MR will be 23 times 2 plus 12 plus 3 16, and then plus N H2O, so that will be 18N, and this is actually equals to 0.0976. Okay, so we solve for N because one equation, one unknown, and we are going to get 10. Okay, so ensure that, just make sure you punch your calculator and check if you can get the value N equals to 10. Okay, next we're going to move on to back titration. Okay, back titration is not something which is very unfamiliar to you. You might have encountered it before, maybe in secondary school, especially in those guided inquiry or alternative assessment kind. So it's not new, but it might not be introduced to you as back titration. So for H2 Chem, we introduced to you as this term known as back titration. So what exactly is happening is that you will add excess of one reagent to react away an unknown amount of that unknown reagent, and then after that you determine the amount of excess you have added by titrating it with another reagent. So usually we call this C, the other reagent. And then after that, you take the difference because you know what is the bulk amount you add, and then you'll be able to find out the amounts which reacted with the unknown B. Yeah, then from there you can determine the amounts which reacted with B. Yeah, so this sounds kind of complicated. So maybe the best example, which could definitely help everybody understand, is to talk about limestone. So you know that limestone rock. So let's say you have a rock here. So this is limestone. So limestone. So limestone is what we call calcium carbonate. It contains calcium carbonate. So let's say we have a certain mass of limestone. So let's say 50 grams. So we have a certain mass of limestone. We don't know how much of it is calcium carbonate. And you may be able to make this stone into a powdered form, but it doesn't really make sense to titrate with solid. You get what I mean? Like titration is usually with solutions. You don't titrate with solids. Yeah. So although you pound it up into powder form, but you can't really titrate it. Yeah. So the first thing you might want to do is because limestone is largely calcium carbonate, and you want to find the percentage of calcium carbonate present in your limestone. So let's say your aim, so let's say your aim is to determine percentage of calcium carbonate in limestone. Okay, for example, so let's say this is the ultimate aim. Okay, then what should you do? Okay, I think the first thing you might want to do is maybe in a huge beaker, you put your powdered limestone over here. So you put your powdered limestone. Yeah, and then you add in excess hydrochloric acid, for example. So introduce excess hydrochloric acid of a certain concentration, but you need to predetermine your excess, so you cannot anyhow just pour. So maybe let's say 100 cubic centimeters of 1 mole per liter. How do you know that this is an excess? Well, you can always do a calculation. So you can always assume that all the 50 grams are all calcium carbonates, which is definitely not the case. And then after that, you determine what is the exact amount of HCl that you need, and then after that, you add a bit more. So let's say the exact amount you need, just a ballpark figure, let's say 85 cubic centimeters. So you just use 100. And 100 is easy to introduce. You can either measure it using measuring cylinder, or if you want a greater accuracy, maybe a pipette or a burette. Yeah, then after that, right, you know your limestone is a lot of powder, right? So a lot of other stuff that we have with the HCl. So later on, you need to filter this solution. Yeah, so as to get rid of the powder. Then after you filter the solution, you will notice this. So let me show you a model. Maybe I think a model here works. So let's say you have this HCl. Okay, so this huge amount of HCl excess. Yeah, so this is the portion. Okay, this is the portion which reacted with limestone. So this reacted with limestone. I mean, sorry, maybe limestone it's quite crappy. So that's calcium carbonate, for example. Okay, and then after you filter it in, right, what you have will be the remaining, right? So this will be the remaining. So this is the remaining, which is the excess. Okay, so this amount, right? Yeah, it's up to you. You can, from the solution, you can top it up with deionized water until the 250 cubic centimeters mark, 100 cubic centimeters mark, depending on you. And then, because it's HCl, you can titrate a fixed volume. So let's say titrate a fixed volume. The fixed volume could be 25.0 cubic centimeters with a known concentration of NaOH. So the known concentration of NaOH is what we call a standard solution. Yes, then after that, you will be able to determine the amounts of sodium hydroxide, and then after that, you can calculate what is this portion. Okay, and then because you know the whole thing, you take the difference, you'll be able to find out the amount which reacted with calcium carbonate. And then you are able to write a balance equation between calcium carbonate and HCl. You will be able to determine the amount of calcium carbonate which reacted with the HCl. And then you will check out whether this mass, you will take that mass, divide by 50, and then that will be the percentage of calcium carbonate present in limestone. Yeah. So if you are thinking about it this way, right, essentially you understand what exactly is called back titration. Yeah, okay, so everything written here I think is a bit confusing. So basically the main idea is, the reason why you want to do back titration is your unknown reagent, right? You cannot really easily react it with the reagent you have in mind. In this case, you can't really react limestone directly with HCl, so that is why back titration is a very useful technique. Okay, so I hope you understand that. I think it's a bit confusing, but yes. Okay, now let us look at exercise 3.4. Okay, so we have a sample of impure magnesium. You analyze it by allowing it to react with excess HCl. Okay, again, keywords is important. Impure. Okay, impure is the keyword. Yeah, excess HCl is another term you need to know. So once you see something like that, then you know that back titration is coming lah. Yeah, so definitely you cannot find out the number of moles of magnesium from here because this 1.32 gram contains some other stuff. Okay, and this is pretty standard. So this is a known amount of HCl. Okay, and then you were told that the remaining solution requires 50 cubic centimeters of 0.250 moles per liter of sodium hydroxide for complete neutralization. Then usually we need to tell you that the impurity does not react with the acid. So they ask you what is the percentage mass of magnesium in the sample. Yeah. So I think this should be straightforward enough. Yeah. Okay. So first of all, we find out the amount of excess. Excess HCl. So amount of HCl excess. Okay. Is actually equals to 0.050 divided by 0.50. Okay, and I'm going to get 0.0125 moles. Okay, you can either call it the excess HCl or the unreacted HCl. It doesn't really matter, but as long as you know what it means. Okay, then from here, because you know the total amount of HCl added, so you can easily calculate the amount of HCl reacted with magnesium. Okay, so that will be 0.100, that's 100 cubic centimeters by the concentration. You subtract it from 0.0125. Okay, so here I'm going to get 0.0625 moles. Yeah, and pretty much that's about it if you can understand it this far. Yeah, okay. But we need to continue to calculate the amount of magnesium that reacted with HCl because they might not react in a 1:1 ratio. So you really have to be very careful about it. So it will be excellent if you can write a balanced equation between magnesium and HCl. Then you realize that they react in a 1:2 ratio. Okay, plus H2 gas. So it's a displacement reaction. They react in a 1:2 ratio. So in that case, we can easily calculate the amount of magnesium present by dividing this value by 2. Okay, and then from that amount of magnesium, we can multiply by the relative atomic mass of magnesium and then divide by 1.32 grams. We'll be able to get the percentage by mass of magnesium. Okay, so we can do that in one step, percentage mass of magnesium. Okay, so this is simply 0.0625 divided by 2 times the relative atomic mass, 3 divided by 1.32, 100%. Okay, so if you punch your calculators, you will get 57.5%. Okay, the question can be made harder by having two different methods, but usually we don't do that unless we want to test you on solving simultaneous equation, which is highly possible sometimes. Okay, next we'll move on to question 2. So we have 1.60 grams of a metallic oxide MO. So M likely to be +2 oxidation state, yeah, because it's 1:1 ratio with oxygen. You dissolve it in 100 cubic centimeters of 1.0 moles per cube of HCl. Yeah, so from here, be aware that some of the MO will have reacted with the HCl. Yeah, so you can easily write a balance equation between MO and HCl. So MO plus HCl, you get MCl2 plus H2O. So this is in a 1:2 ratio. Okay, then so there will be some excess, likely to have some excess HCl remaining, and that is why the resulting liquid you top it up to 500 cubic centimeters, and then you abstract 25 cubic centimeters out, and then you realize that this is the volume of sodium hydroxide of a certain concentration for complete neutralization. Okay, so the first thing that you might want to do now is, I think first you can calculate the amount of H plus in excess. So we do the same thing. So amount of H plus in excess, okay, which is equals to 0.02105 multiplied by 0.1020. And then remember to scale it to 500. Yeah, because this is quite important, because if you forget to scale, then actually a lot of things can't be done. What do I mean by scale to 100? Oh, sorry, 500. That's because from the 500, you only take out 25. Yeah, so in this case, I must scale to 500. So divide by 25 times 500. Okay, so this will be the amount of H plus in excess. So that will be 0.04294 moles. Okay, then you can easily calculate the amount of HCl you have initially. So from here, you can easily determine it 0.100 moles. Okay, then you can easily calculate the amount of HCl reacted with MO. Okay, so that will be the difference between 0.100 with 0.04294, and then you should be able to get 0.05706 moles. From the balance equation, MO and HCl reacts in a 1:2 ratio. So therefore, from the amount of HCl reacted, you can easily determine, let me use a different color, the number of moles of MO, which is 0.05706 divided by 2. Okay, so from here I can take calculator and punch in the numbers. So 0.05706 divided by 2. So I will be able to get 0.02853 moles. Okay, so from here, you can easily determine the relative formula mass of the oxide by dividing 1.6 by 0.02853. Okay, so MR of MO is equals to 1.60 divided by 0.02853. Okay, so I'll take the calculator and punch it 1.6 divided by 0.02853. I'm going to get 56.1. Yep, and then I can get the AR of M. So AR of M essentially is 56.1 minus 16. So I will get 40.1. So 40.1 is actually calcium. Yeah, so the unknown metal is calcium. Okay, I think I skipped part 1. So part 1 actually requires you to calculate the mass of the oxide that reacts with 1 mole of HCl. So in that case, I can simply just take 1.6 divided by 0.05706. Okay, so when I do the division, I should get 28.0 grams. So 28.0 grams of metal oxide reacts with 1 mole of HCl. Okay, so with that, we'll move on to exercise 3.5. Let me just erase this portion so that it's clearer, so that it will not obstruct your views. Okay, so for exercise 3.5, what we have is we have a sample of ammonium chloride. I warm it with 100 cubic centimeters of sodium hydroxide. So you know that ammonium is actually an acid. So ammonium and sodium hydroxide will react and process the gas plus H2. So after all the ammonia has been driven, the excess sodium hydroxide requires this volume of sulfuric acid for neutralization. You notice they purposely use sulfuric acid, okay, for a similar reason, because you need to do conversion. You can, it's not just 1:1 ratio. Yeah, but of course, if you are very sharp, you know that one equivalence of sulfuric acid contains 2H plus. I think that would be relatively straightforward. Okay, so yeah, what we can do is number of moles of we can easily calculate the amount of excess hydroxide, okay, by taking the volume of sulfuric acids multiplied by the concentration. Remember to multiply by 2. Okay, so this will be the amount of excess OH minus. We'll get 0.0250 moles. Okay, so with this excess amount of OH minus, we will take the difference between whatever we have at the start. So therefore, the number of moles of OH minus reacted with ammonium chloride, okay, it would then be equals to 0.100 multiplied by 0.00 multiplied by 0.0250. So here we'll get 0.0750 moles. Okay, and you know that they react in a 1:1 ratio. So this is also equals to the amount of ammonium chloride. Yep, so the mass of ammonium chloride is simply the amount multiplied by the relative molecular mass, or relative formula mass to be more exact. So that's 14 plus 4 plus 35.5. Okay, so I should be able to get 4.01 grams. Right. Okay, so I think that will be the end of section 3. Okay, so the next section is section 4 on redox reactions, which you would have encountered in secondary school. So for redox reaction, it's made up of 2 terms, reduction and oxidation. Okay, so basically we define it by looking at the change in oxidation states due to electron transfer. I think that would be the simplest definition for H2 chem and beyond. Yeah, so in fact in university we solely look at how the change in electrons, or how the exchange of electrons between 2 parties will cause increase and decrease in oxidation states. So for example, for copper 2, in our case here, it's likely to be a reaction which occurs at the cathodes. So if you remember from electrochem when reduction took place, so copper 2 is reduced to copper. Yeah, so in this case, 1 mole of copper 2 gains 2 moles of electrons, and you get 1 equivalent of copper. Yeah, oxidation is where the species, in this case metal, usually metals lose electrons, so metal loses electrons to give you zinc 2, and 2 electrons being lost. So for every 1 equivalent of electrons being lost, there will be 1 equivalent increase in oxidation states. Yeah, don't really need to memorize as long as you are confident about the concepts. Okay, reducing agents and oxidizing agent, I don't think they need introduction. So basically, reducing agent is the agent which performs the reduction, but they themselves get oxidized. Then oxidizing agent is the reagent which performs the oxidation, but they themselves get reduced. Yeah. H2 chem introduce you to a special kind of reaction called disproportionation, where the same substance is both oxidized and reduced. Okay, so in our case, in our example here, chlorine in the presence of an alkaline medium will disproportionate to chlorate and chlorate 5. Okay, so this is known as disproportionation. You can easily calculate the oxidation state of chlorine here by just letting it be X, and then oxygen in this case -2 each, so that will be -6 equals to -1. So X is equals to +5. Yeah, so the reverse of this proportionation is known as comproportionation, where two species of the same substance react to give you the same oxidation state. Yeah. Then, so for oxidation states, here we are looking at the fundamental principle of calculating oxidation states. We need to be mindful that the fundamental principle of calculating oxidation state is first by assuming a perfect ionic model. Okay, what do we mean by assuming a perfect ionic model? So, for example, the more electronegative element will take all the electrons, even in a covalent compounds. Yeah, so that is how we assign oxidation state. So, for example, in H2O, if we draw the dot and cross diagram, this is what you're going to get. For the more electronegative element, in this case is oxygen. So if you assume that you draw a boundary here, you box it up. So if it takes all the electrons, so there will be a total of 8 electrons. So originally oxygen has 6 electrons, now it has 8. So you'll take on the oxidation state of -2. For hydrogen, originally it has 1 electron, now it has 0 electrons, so you'll take on the oxidation state of +1. Yeah, so in secondary school, we tend to memorize things such as oxygen will always take on oxidation state of -2, except peroxide, where it takes on oxidation state of -1. There isn't a need to memorize such thing ever again after you understand the fundamental model. Yeah, because here, for example, in H2O2, if you draw a dot and cross diagram, and then you assume a perfect ionic model. So oxygen will take all the electrons, but between two oxygen, there is no preference, so it will take back their own electrons. So altogether, the central oxygen here being highlighted in orange, you have 7 electrons, so one excess of 6, so oxidation is -1. So H is also +1. Yeah, so that is why H2O2, the oxidation state of oxygen is -1 instead of -2. Okay, so I hope a simple introduction like this helps you to understand why oxidations, I mean the fundamental principle of calculating oxidation state. So there isn't really a need for you to memorize oxidation states once you understand the principle behind it. Okay, so the assignment of oxidation state, usually the more electronegative element will take on a lower oxidation state. I don't think I need to go into details, so you can read through everything, pretty much similar to what you have studied in secondary school. Okay, yeah, so again, all this, there are many exceptions lah. So oxygen is not only -2 and -1, it could be say -half, for example, in superoxide. So yeah, so there isn't, I mean, all these are just general list which you can look at. And hydrogen is also not always +1. If let's say it's bonded to a less electronegative element such as a metal, so it can take on -1. Yeah, so just take note that this list is not exhaustive. Yeah. Okay, so let us use first principle to try to calculate the oxidation state, let's say for ethanol. So for ethanol, if you want to use first principle, I think the first thing you need to do is to draw the dot and cross diagram. So we can do a quick one over here. So we have carbon, H, and then carbon here, H, H, and then O, and then O. Okay, so if you assume a perfect ionic model, carbon is more electronegative than hydrogen. Yeah, so over here we'll cut into half. Okay, so we'll just cut into half like this. Okay, so we just draw the boundary, and then the other carbon we'll draw it like this. Okay, Why is it this way? Because carbon is less electronegative than oxygen. Okay, so with that, let us assign the oxidation state. So the carbon on the left, oxidation state, altogether 7 electrons here, in excess of 3, so minus 3. Okay, the one in the middle, 1, 2, 3, 4, 5, in excess of 1, so minus 1 oxidation state. Yep. If you want to calculate an average oxidation state, that's fine also. So what you can do is for ethanol, you let the oxidation state of carbon be X. So you have 2X. Altogether, there are 6 hydrogens, so plus 6, plus 6 minus 2 equals to 0. Okay, so you shift the thing around, so X is equals to minus 2. Okay, so minus 2 is actually the average oxidation state of carbon. Okay, take note of this. Yeah, so you can easily verify it by taking an average of minus 3 and minus 1, you get minus 2. All right. Okay, so I hope this little exercise helps you to understand redox and determining oxidation state a little better. Okay, so we have exercise 4.1, supposed to determine the oxidation state of the underlying element. So again, we can let this be x. So x plus 4 minus 2 equals to 0. So in this case, x equals to minus 2. Okay, we can do that quite easily. Elements will always be 0, so don't need to calculate. BrF3, fluorine is more electronegative than bromine. So in this case, bromine will be plus 3 because it's bonded to 3 fluorine. And HNO2, similar story. So you have plus 1 plus x minus 4 equals to 0. So x is equals to plus 3. Okay, so we can do that quite easily. Calcium hydrogen carbonate, we actually don't need to take the whole ionic compound. We can just focus on hydrogen carbonates. Okay, so when you focus on hydrogen carbonate, H is simply 1 plus X, okay, minus 6 equals to minus 1. So in this case, X is equals to plus 4. Okay, so hydrogen carbonate, the carbon has an oxidation number of plus 4. Okay, we'll move on to exercise 4.2 now. So you are asked to identify the reaction represented in the following equations. So which are the reducing and oxidizing agent for the redox reactions? Okay, now first of all, we need to determine if they are indeed redox. Okay, how shall we do that? We check out for change in oxidation states. So the simplest way is to look at obvious elements. So we have zinc here, zinc is 0. So you know that zincates plus 2 oxidation state for zinc. You can easily calculate that because OH is minus 1. So you know that zinc is being oxidized. So if zinc is being oxidized, something must be reduced, right? So let's check. So we have nitrogen because nitrate here, and there's no nitrate on the right hand side. So the nitrogen here should be plus 5. And then the nitrogen here would be plus 3. No, sorry, minus 3. Okay. So in this case, zinc is being oxidized from 0 to plus 2. Nitrogen is being reduced from plus 5 to minus 3. So this is indeed a redox reaction. Okay, then after we identify the redox reaction, the next thing we need to do is identify the oxidizing and reducing agents. Yeah, so oxidizing agent is obviously nitrate here. Okay, because I'll just let it be OA. Okay, so this is Ra, reducing agent and oxidizing agent. Reducing agent will be metal. If you are sharp enough, you know that most metals are reducing in nature. So definitely they are reducing agents. So then other range will be oxidizing. Okay, yeah. For part 2, you notice just from left to right, potassium remains as plus 1, chloride remains as minus 1, silver remains as plus 1, the nitrogen remains at plus 5. So there's no change in oxidation state. So this is not redox. So not redox. Yeah, but you learn it. You learn a special name. This is known as precipitation reaction. Okay, so it's precipitation. Okay, acid-base reaction is also not redox. Yeah, because there's no change in oxidation state. So the full name is acid-base neutralization, or you can simply just call it acid-base reaction. For part 4, there's an obvious change. Iron +2 to +3, so this is oxidized. And then H2O2 oxygen goes from -1 to -2, being reduced. Okay, so in this case, H2O2 is the oxidizing agent, iron 2 is the reducing agent. Okay, so this is a redox. Okay, so oxidizing agents and reducing agents. Okay, now we come to the most important part, which is on the balance of redox reaction. So with this, for this part, I'm just going to use the blank sheet of paper to explain. If you wish to, you can read through your notes because your notes have a long list of description which you have to go through, which I'm not going to discuss it with you directly. Okay, what I could do is I could use exercise 4.3 to explain to you. But before that, I think let me just teach you how to balance using a blank sheet. Okay, so the simplest way to balance redox equation. So let us look at a very familiar reaction using permanganate, potassium permanganate as the oxidizing agent. Okay, so permanganate, when it is behaving as an oxidizing agent, it will be reduced to Mn2 plus. So one of the fundamental way to balance redox equation is to look at the change in oxidation states, because the change in oxidation states here allows you to determine the number of electrons being transferred. Okay, so manganese here, oxidation state +7, manganese here +2. So in order for it to be reduced from +7 to +2, it must take in 5 electrons. So I'm going to put 5 electrons on the left hand side. Yeah, so that's the first principle. Find the change in oxidation states of the respective species, and then after that incorporate the electrons in. Okay, so in this case, in order to be reduced from +7 to +2, permanganate needs, the manganese in permanganate needs to take in 5 electrons. And then after that, we need to determine, we need to incorporate either acids or hydroxide in order to balance the charges. Okay, because redox reaction, they occur either in acidic or alkaline medium. Yeah, so in acidic medium, you use H plus. In alkaline medium, you use OH minus. Yeah, so with that, let us calculate the total charge. So the total charge on the left hand side is -6. The total charge on the right hand side is +2. So in order for the charge to balance, I need to add 8 H plus here. Yeah, because +8 minus 6 is equal to +2. So principle number 1, charge must balance. Yeah. Just now I forgot to say one thing because conveniently it's already balanced. Material must also balance. So if I want manganese on the left, I must have one manganese on the right. Yeah. So there are two principles when it comes to redox balancing. One is there must be material balance or mass balance. The second principle is the charge must balance. And you balance charge using H plus, okay, or OH minus, depending on the medium. Okay, yeah. So after that, you will realize that water will balance itself miraculously. Yeah, okay, it's not really miraculous, but because we have already balanced the necessary, the materials we need. Okay, so we have 4 O's on the left and 8 H on the right, sorry, on the left as well. So in this case, I will balance water with 4 H2O. Okay, so from here, I just want to bring your attention to the data booklet. Some of the redox half equations, we call these half equations because it involves electrons, are present in the data booklet. So you might want to look at them from this particular list. So for A, they are in alphabetical order. So you just go to M, okay, and you can see it over here. Okay, MnO4 minus plus 8H plus, you get Mn2 plus plus 4H2O, and this is your answer over here. You can see. Okay, so if you wish to do some practice, you can just pick up any half equations, and then after that you practice, and then after that you check your answers. Okay, but what I've written here, right, it is simply let me just box it up. This thing is simply what we call the reducing half equation, reducing or the reduction half equation. Yeah. A redox equation will not be balanced if you don't know the counterparty. So in this case, usually permanganate, we use it, if you can remember from your practical, we use it to oxidize iron 2. Okay, so in this case, iron 2 plus will be oxidized to give us iron 3 plus. Okay, and then first, mass balance is the most important. So we have one iron 2 on the left, one iron 3 on the right, so that's fine. Then next, we look at the change in oxidation state. So from +2 to +3, in order for it to reach +3, it must give out one electron. And then now everything else is balanced because we don't have to introduce H plus. The reason being there is no, it's not an oxo anion or cation we are talking about. Yeah, if you look at permanganate, the reason why we need to introduce oxygen and hydrogen is because we are dealing with a polyoxo anion. Polyoxo means that the metal center contains oxygen. Okay, so in that case, the oxidation half equation for iron is already balanced. This is the oxidation half equation. Okay. Then in order to write out the full balance equation, we just need to add the two up. So how do we add the two up? When you add the two up, make sure that the electrons cancels out. Okay, how do we ensure that? Okay, so for the reduction half equation, you notice that the electrons are on the left hand side, so that's 5 in total. Oxidation half equation, you notice that the electrons is on the right hand side, that's 1. Yeah, so you will multiply the oxidation half equation by 5. So if you multiply by 5, so you have 5 here, 5 here, 5 here. When you add the 2 up, the electrons will cancel out. Okay, and that gives you the balanced redox equation. So we're going to get MnO4 minus plus 5 iron 2 plus plus 8 H plus, and then I will get Mn2 plus plus 5 iron 3 plus plus 4 H2O. Yeah, so this is what you need to do. Okay, so in short, first write out either the reduction half equation or the oxidation half equation, or rather you need to write both. Then after that, ensure that for the reduction half equation, the electrons is on the left, oxidation half equation, the electrons is on the right. Then make sure that they are balanced by multiplying with the appropriate stoichiometric coefficients. And then when you add both equations up, make sure your final equation does not have any electrons. And that's about it. Yeah, so that is what we call balanced redox equation using the half equation methods. Okay, however, sometimes half equation method can be quite slow because you need to write the individual half equation out, which may not be I mean very time appropriate, because sometimes in exams or when we are doing work, we need to rush through them. Yeah, so sometimes writing half equation is not that intuitive. Yeah, so over here I'm just going to show you another way of doing. You notice that it's actually similar, but it's just that I'm not going to write out the half equations, so I'm just going to balance it directly on the equation itself. Okay, so again I'm going to use the same example, which is permanganate and iron 2. Okay, so you see if this method works for you. If it doesn't work for you, just use the half equation method. It will almost always work. Okay, yeah, so first I'm going to write out permanganate. So MnO4 minus plus iron 2 plus Okay? Then I'm going to draw an arrow. Then I'm going to get Mn2 plus iron 3 plus. Of course, the assumption of this method, when we just write the balancing out straight away, right? The assumption is that you know the products. Yeah, because honestly, if you don't know the product, you can't even do anything. You can't even do the half equation. So you must know the product in the beginning. Okay, then after that, you have to be systematic. Okay, now please follow my thought process. Okay, manganese oxidation state is +7 on the left. The reduced product is +2. Okay, so in order for it to go from +7 to +2, permanganate needs to gain 5 electrons. Okay, in order for iron to be oxidized from iron 2 to iron 3, it needs to lose 1 electron. Okay, so now this is the catch. Permanganate needs to gain 5. Iron 2 needs to lose 1. Yeah. And where does permanganate gains the electron from? From iron 2. But iron 2 can only lose 1. So how can permanganate gains 5? I will need 5 iron 2. So if I have 5 iron 2 plus here, then I need to balance the material. So there will be 5 here. Yeah. So once you are done with this, you are almost at the end of your journey, because that's it. That's almost it, because you don't need to write out the electrons anymore, because you have already accounted it by going through this thought process. Okay, then after that, the next thing you need to do is balance the charge. Remember, material balance comes first, then charge balance. Okay, so this is likely to be done in the acidic medium. Okay, as mentioned before, so acidic medium. Okay, so in the acidic medium, we balance the charge using H+. So the total charge on the left-hand side will be +10 minus 1, so +9. The total charge on the right-hand side will be -15 plus 2. So that would be minus, oh, sorry, there's a plus, so sorry, what am I talking about? Yeah, +15 plus 2, so that's +17. Okay, so from +9 to +17, I need to add 8H plus. So I will add 8H plus here. And then, of course, like what I mentioned earlier on, the H2O will automatically be balanced. So from here, you get a +4H2O. And then that's it. You notice that you get the same answer. Okay, these two answers are the same. Okay, so if you like this method, let us try out in the exercise 4.3 in your lecture notes. Okay, now, so we take a look at the medium. So acidic medium. Okay, so we have acidic medium here. Okay, so first, I think I will just write it on top so that it's a little bit bigger, so you can see. So Cr2O7 2- plus iron 2 plus, I will get Cr3 plus Fe3 plus. Okay, I'm not going to do the individual half equation method. I'm just going to do it directly. Okay, so if you do a quick calculation of the oxidation state of chromium here, it's actually +6. Okay, but please take note that there are 2 chromium. Okay, so I'm going to write a 2 here. Okay, just to ensure that there's a material balance. Okay, so from +6 to +3, so that means each chromium will lose, or rather each chromium will gain 3 electrons. So 2 chromium will gain 6 electrons. So gains 6 electrons. And then where does it gain it from? It gains from iron 2 plus. So iron will loses 1 electron. Yeah. So that means that I need 6 iron 2 plus in order for me to provide dichromate, which is Cr2O72 minus the 6 electrons. Yeah, so we have a 6 here, and that's about it, right? So you already get the basic form out already. So the remaining thing you need to do is to balance the charge. Okay, so the total charge on the left hand side will be plus 12 minus 2 is plus 10. So plus 10 on the left, plus 18 plus 6. So that's plus 24. So I will need 14H plus. So in this case, I will need to introduce 14H plus. Okay, then after I introduce 14H plus, I need to balance the remaining with water. So it's 14H and 7 O's. So in that case, I will have 7H2O. Yep, and pretty much that's about it. Okay, in case you're wondering why H plus, because it's acidic medium. Okay, yeah, if you are not comfortable with this method, by all means, please try out the half equation method. Okay, both works wonderfully. Okay, now next we look at the basic medium. Okay, so for the basic medium, we have chlorine here. So it's a disproportionation reaction to give us chloride and ClO3 minus. Okay, so now we look at the oxidation states. So we have two chlorine here. So each chlorine 0. Okay, 0. I just put 0, 0. So this is minus 1 and plus 5. Okay, so that means one of the chlorine will be reduced to minus 1. Okay, and then the other chlorine will be oxidized to plus 5. But you notice that it's a bit weird, right? Because in order for chlorine to be reduced to minus 1, it needs to gain 1 electron. But in order for chlorine to be oxidized to plus 5, it needs to lose 5. Yeah, but chlorine can't lose 5 because I'm not getting Cl5 minus. Yeah, or rather, I'm not getting, or rather, it can't gain 5 because I'm not getting Cl5 minus. Yeah, so what can it do? Okay, so let's take a look this way. So we have a Cl that wants to reach plus 5. So it will lose electrons. So one of the Cl will lose 5 electrons. Just imagine, I will lose 5 electrons in order to reach plus 5. Okay, so one of the Cl will lose 5 electrons. But this 5 electron cannot be gained by the other Cl. Remember it's Cl2, right? So I have one Cl, like it's like Cl2, so I have one Cl on the left and one Cl on the right. So the other Cl cannot gain 5 because it cannot reach minus 5 oxidation states. Yeah, however, it can reach minus 1. So therefore, Cl will lose 5 electrons to 5 Cl. And then each of these Cl become minus 1. So if you do a quick summation, right? 5 plus 1. So I need 6 Cl in total. Yeah, but I have Cl2, so therefore it's 3 Cl2. Yeah, do you get that? And then eventually these 5 Cl become minus 1, so it's 5 here. Yeah, so once you get the ratio correct, because it's basic medium, total charge on the right hand side is minus 6. So in this case, I will need 6OH minus. Okay, and then if I do a quick balancing with water here, I have 6 O's and 6 H on the left hand side. And then right hand side, I will have 3 H2O. Okay, so in case you are confused, the final equation is simply 3Cl2 plus 6OH minus. I will get 5Cl minus plus ClO3 minus plus 3H2O. So this is the balanced equation for exercise 4.32. Okay, if you are still confused, it's fine. Please go and write out the half equation. I think it's usually easier for most students. But if you can do it straight away on the spot, like what I've done, I think it saves you a lot of time. Okay, so next we'll move on to this part, which teaches you how to balance equation without splitting the half equation. Essentially is what I've mentioned. Again, it's a lot of rules. If you wish to, you can write it. If not, I mean, you can read it. If not, if you have already understood what I'm trying to say, I think it's fine. Okay, right, and then yes, we'll move on to 4.4. I think this will be more direct. So we have H2O2 I minus acidic medium. So let's try. Okay, so again, let me write on top. H2O2 plus I minus, I'm going to get I2 plus H2O, but I'm going to write 2H2O. Why do I write 2H2O? Remember, material balance. Yeah, so I have two O's here, and then I need to have two O's. Okay, then the next thing I'm going to do is I'm going to look at the oxidation state of the oxygen. So the oxygen here is -2. So this is -1. So in this case, oxygen actually gains 1 electron. So altogether, the oxygen will gain 2 electrons. Okay, altogether. So for the so each oxygen gains 1, so oxygen will gain 2. And these 2 electrons must come from I minus, because in order for me to go from -1 to 0, each I will lose 1 electron. So therefore, I have 2 I minus here. And then because it's acidic medium, I need to introduce H plus. So therefore, I will add 2 H plus. Yeah, and this is the balance equation. Okay, we don't have to add water because the product of H2O2 is water. So that's fine. Okay, so question 2. So for question 2, we have this interesting molecule, technetium. So TCO4 minus plus arsenic, okay, in basic medium. So I'm going to get technetium here plus AsO2 minus. Okay, just going to rewrite the S so that it looks an S. Okay. Right, so let us fill in the oxidation state because these are pretty unknown elements. So technetium here will be +7, arsenic 0, technetium here 0, arsenic here would be +3. Okay, so again, same story. Technetium will need to gain 7 electrons. Arsenic will need to lose 3 electrons. Okay, so one needs to gain 7, the other one needs to lose 3. So again, simplest way, we cross multiply. So we have 3 here and 7 here. Okay, basic medium, we need to add OH minus. So total charge on the left is -3. Total charge on the right, okay, it's not balanced yet because remember you need to balance the material, right? So when we add 3 and 7, so we need to add in 3 here and 7. Okay, and total charge on the right is -7. Yeah, so in order to balance the charge, we need to add 4OH minus to the left hand side, so plus 4OH minus. Okay, and altogether we have 12 plus 4, 16 oxygen on the left. We have 14 oxygen on the right, so in this case plus 2H2O. Okay, the 4 H's comes from OH minus. Yep, and we get a balance equation. Okay, next we are going to look at section 4.4 on redox titrations. Okay, so similar to acid-base titration, for redox titration, you have a known concentration of oxidizing agents, and then you use it to find an unknown concentration of reducing agent or vice versa. Okay, so you might want to know the common color of oxidizing agents such as permanganates and dichromates. And permanganate is only it can be present in both acidic and alkaline medium, but the product will be different. So these are some of the stuff which you need to be familiar with. Even if you are not familiar with them, it's fine because through doing the practicals, you become more familiar when you look at the color changes. So for dichromate, it only exists in acidic medium. The final product is chromium 3+, which is green in color. But you're not going to do this in school because chromium reagents are banned. Yeah. If you are wondering what about alkaline medium you won't get dichromates, but you'll get something called chromates 6. Okay, which looks like this, CrO4 2 minus. Okay, so for iodine, as a neutral medium, so usually it appears brown. It won't be a precipitate form. Usually when you see precipitate, that means you do not have enough iodine. Yeah, so again, we have iodides to complex with iodine to give us I3 minus, which appears brown or yellow in color. So you might want to know the brown color or the yellow color of iodine in aqueous medium is due to I3 minus. Okay, H2O2 is also an oxidizing agent. It could be both oxidizing and reducing depending on its partner. Yeah, so yeah. Then for common reducing agent, iron 2, I minus, thiosulfates, H2O2 as well, and ethane diolates. Okay, so this is quite common. So this is known as oxalates, okay, or ethane diolates. Okay, so its structure looks like this. It has a carbon O and O minus, so it's like a dicarboxylate. Yeah. Okay, so the full name is ethane diolatic acid. Yeah, but it has a common name known as oxalic acid. Yeah. Usually, permanganate is put in the burettes because if you put it into the conical flask, then the permanganate will be in excess, so the products will be oxidized by permanganate itself. So you want that you want to prevent that from happening. But there are some cases where you put the permanganate in the conical flask as well. So it really depends on the rates of the reaction. Another common category you need to be familiar with is, I think I mentioned earlier on, iodometric titration. Yeah, this will come up very, very often in H2. So it involves reacting iodine with thiosulfates. Yeah, so eventually you get I minus and diolates. Okay, indicator is starch. So the starch will complex with iodine to give you a dark blue complex. Yeah, so when all the iodine have been reacted, then solution will turn colorless. Usually for iodometric titration, a good practice is to titrate all the way until your aqueous solution turns pale yellow. Yeah, so this would be an excellent practice. So the pale yellow should be quite pale. It shouldn't be dark yellow. Yeah, so probably something like a yellow which has this particular shade or even slightly lighter. Okay, then yeah, I think these are some of the stuff which you need to take note of. So there are some of the points to be considered here, so you can read through them. Yeah, usually iodine you need to titrate quickly because they are volatile, so you want to prevent them from evaporating away. And starch indicator cannot be added too quickly because if not, your iodine will be deeply bonded into your starch, and it might take a slightly longer time for them to be reacted away. Okay, sometimes after the titration, there will be a slow return of blue color. Yeah, so there could be a few reasons. It could be due to atmospheric oxidation of iodide to iodine, which could be due to the presence of acid as the catalyst. So if your solution is slightly acidic, it will actually accelerate this atmospheric oxidation. Okay, usually we'll ignore the return of the blue color. You will not continue to titrate after that. Okay, so the first instant of decolorization from dark blue to colorless, you just record that value. Okay, iodometric back titration, you can use that to analyze redox reaction. So I think an example is being shown here. Okay, so usually you add Ki to an excess, or rather excess Ki to an oxidant, and then you will produce iodine. Then from the amount of iodine, you will determine it using thiosulfates, and then you work backwards to determine the amount of oxidizing agent present. Okay, yeah, I think that should be quite straightforward. So I think you need to read through some of the details in order to familiarize yourself with some of the stuff. Okay, so we'll move on to exercise 4.5. The first question. Okay, so for the first question, you are given a fixed volume of known concentration of permanganate, and then oxidized 25 cubic centimeters of H2O2. And in the process, it gives you oxygen gas. Okay, you are told that this is the exact amount of permanganate that is required. Yeah, so from here, what you can do is you can do a quick calculation and convert this to number of moles. Okay, so let's try to do that. So you can try to get the number of moles of permanganate from here, and then you get 0.0275 multiplied by 0.0200. Okay, so from here you will get 5.50 times 10 to the power of minus 4. Okay, then you need to write a balance equation involving permanganate and H2O2. Yeah, since you are given the products, it should be fine. So we can use what we have gone through earlier on. So permanganate plus H2O2. So products will be Mn2 plus O2. Okay, so H2O2 gets oxidized. So in this case, permanganate will need to gain 5 electrons. H2O2 will need to lose 2 electrons. So in this case, you cross multiply. Yeah, so we have 2 here and 5. So that would be 2 and 5. Okay, then you can balance the rest, but actually don't need to balance since you already get the relevant stoichiometric ratio. But of course, in order for us to complete our answer, let's try to balance it. Total charge on the left minus 2, total charge on the right plus 4. So we need to add 6H plus on the left hand side because acidic medium, and then relevant amount of water here, I think it will be 8H2O. Yeah, but the most important ratio we need is 1:2.5. Yeah, because this is extremely crucial here. Yeah, so from here we can determine the amount of H2O2 present, which is essentially 5.50 multiplied by 10 to the minus 4, and you multiply by 2.5. Okay, then you will be able to get 1.375 times 10 to the power of minus 3 moles. Okay, and because I'm using 25 cubic centimeters of H2O2, yeah, then I can easily calculate the concentration of H2O2. So concentration of H2O2 becomes 1.375 times 10 to the power minus 3 divided by 0.0250. Okay, so you are going to get 0.0550 moles per liter cube. Okay, yeah, so that will be the concentration of H2O2. Then what about the volume of oxygen evolved? So the volume of oxygen evolved will be, in terms of number of moles, will be the same because 1:1 here. So this will be the number of moles of oxygen evolved. You need to convert it to STP. So volume of O2 evolved will then be 1.375 times 10 to the power minus 3 multiplied by 27. Okay, so we are going to get 0.0312 pm cube, or you can leave it as cubic centimeters. That will be 31.2 cubic centimeters. All right. Yep. Then let's move on to question 2. So for question 2, we have 0.1576 grams of iron converted to iron 2 and then acidified. Okay, then you titrate it against dichromate of a certain concentration. Given that 27.30 cubic centimeters of oxidant was required, calculate the percentage purity of the iron wire. Okay, then okay, I think the simplest way is for us to calculate the number of moles of dichromates. So number of moles of dichromates over here, it will be 0.02730 multiplied by the concentration, which is 1.64 times 10 to the power -2. So that will give us 4.477 times 10 to the power -4 moles. Okay, so this would be the amount of dichromates. Then the next thing we might want to do is to write out a balance equation involving dichromates and iron 2. Yeah, so we'll do the same thing here. So dichromates plus iron 2 plus, and then we will get 2Cr3 plus Fe3. Yeah, so again, the 2 chromium in dichromates will gain a total of 6 electrons, and these 6 electrons are gained from iron 2, so we have 6 here and 6 here. Yeah, if you want to do the rest of the balancing, you can. So that will be 14H plus, and then 7H2O. Yeah, the most important ratio we need is actually 1:6. Yeah, so from the amount of dichromates which we have calculated, which is 4.477 times 10 to the power -4, we will multiply it by 6, so we will be able to get the number of moles of iron plus, so that will be 4.477 times 10 to the power -4 times 6. We are going to get equals to 2.686 times 10 to the power -3 moles. Okay, then in order to calculate the percentage purity, so what we can do here, just let me erase this. So percentage purity, okay, is simply 2.686 times 10 to the power -3 multiplied by 55.8 divided by 0.1576 times 100%. So over here, I'm going to get 95.1%. Okay, so you notice that redox titration calculation is similar to the normal stoichiometry. The only difference is that we need to be able to write out the balance equation, and that actually requires some skills, which we have earlier on showcased to you how it can be done. Okay, so next we'll move on to exercise 4.6. We have chlorine reacts with iodine to form a compound P, ICl7. Okay, so when dissolved in excess of aqueous potassium iodide, P liberates iodine, which is the only iodine containing product in the reaction. Okay, then the first question they ask you is to calculate the number of moles of iodine liberated when 1 gram of T reacts with excess of Ki. Yeah, okay, then I mean, what we can do is we can first calculate the relative molecular mass of ICl7. Yeah, and then after that, we determine the number of moles present in 1 gram, which is, I mean, what we will normally do. And then you notice that ICl7 to iodine is 1:4 ratio. Yeah, so we can easily calculate that. So therefore, the number of moles of iodine is simply 1.00 divided by, if you sum it out, is 375.4. You multiply by 4. Okay, so you'll get 0.0107 of iodine being produced in this reaction. And then for part 2, what volume of 1 mole per unit of sodium thiosulfate will be required to react with all the iodine in part 1? Okay, so you know that thiosulfate's formula is S2O3 2-, and then reacts with iodine. The products is S4O6 minus plus 2I minus. In case you are wondering where can I get this from, it's actually in your data booklets. So thiosulfates is over here. Yeah, but just ensure that you write them out in the wrong side of the equation. So thiosulfate is the one on the right hand side, S2O3 2 minus to give you S4O6 2 minus. 2 electron is given out. Okay, yeah. So with that, each of the iodine will gain 1 electron. So therefore, I will need 2 of this. Yeah, because each sulfur will, or rather, a combination. Okay, S2O3 2 minus. When it gives you S4O6 2 minus, to balance the material, in this case sulfur, I will need 2 equivalent of S2O3 2 minus, and this actually gives out 2 electrons. Yeah, and these 2 electrons are being gained by iodine to give you 2 I minus. Yeah, so it's in a 1:2 ratio. So in this case, from here, I can easily calculate the amount of thiosulfate needs. So essentially, it's 0.0107 times 2. So I'm going to get 0.02132 moles. Okay, then the volume of thiosulfate I need is equals to 0.02132 divided by 1.00. So that will give me 0.02132 dm cube. Essentially, it's 21.3 cubic centimeters. Okay, this is a pretty straightforward calculation. I think it's a lot easier than exercise 4.5, but yeah, it's fine because not all exercises needs to be difficult. Okay, then we have a 4.5 here, application of oxidation number and electron transfer. I think the easiest way is to look at the question and then we will discuss from there. Okay, then we have question 1 from exercise 4.7. So in an experiment, I have 50 cubic centimeters of 0.1 moles per dm cube solution of a metallic salt. So this is an unknown. Reacted exactly with 25.00 cubic centimeters of a 0.1 moles per dm cube of sodium sulfite. Okay, you are given a half equation for the oxidation of sodium sulfites or sulfites. Sometimes they will give you the half equation, especially so if it's not given in the data booklet or they don't need you to derive it. So if they give it to you, I think it's good, just use it. So you were being asked if the original oxidation number of the metal in the salt was +3, what would be the new oxidation state? Okay, yeah. So so a general strategy is, I think, first of all, let us try to determine the amount of sulfides present. Okay, so just going to highlight this. So from here, I will be able to determine the amount of sulfides present. Okay, so that will be 0.050 multiplied. I will be able to get 0.0050 moles. Okay, then you notice that for every 1 equivalent of sulfides, it gives out 2 equivalent of electrons. Yeah, so therefore the number of moles of electron transfer will be equals to 0.0050 divided by 2, which is equals to 0.00500. Okay, and this number of moles of electron transfer will be transferred to the metal salts. Okay, so I need to calculate the amount of the metal salts. Sorry, I should have underlined. Okay, so I will need to calculate the amount of the metal salts. Okay, I can easily do that by calculating the amount of the salts. Yeah, so the amount of M3 plus is equals to 0.050 multiplied by 0.1 is equals to 0.0050 moles. How do I know it's +3? Because we were told that initially it's +3. Okay, then from here, we will take a ratio. So in that case, the number of moles of M3 plus to the number of moles of electrons is actually 0.00500 is to 0.00500. So that is 1:1 ratio. So that means that one equivalence of M3 plus gains one equivalent of electrons. Yeah. So because of that, it will be reduced to +2. So therefore, the final oxidation state is +2. Yeah. So that is how you go about working on the problems. Okay. Then for question 2, you have 25.0 cubic centimeters of a solution of potassium ethane diolate. Okay, so remember this ethane diolate which I mentioned earlier on. Okay, so worth to pay a little bit attention to. So this is the ethane diolate. So what we're going to do here is we will calculate the amounts of ethane diolate from here. Okay, so we're going to calculate the amount. So amount of ethane diolate C2O4 is actually equals to 0.0200 multiplied by 25, sorry, 0.025. Okay, so if you do a quick calculation, you will get 5.00 times 10 to the power minus 4 of ethane diolate. Okay, you were told that it reacted with 20 cubic centimeters of 0.01 moles per little cube of permanganate. Okay, so let us calculate the amount of permanganate here. Okay, so I'm going to calculate in green, sorry, in orange. So amount of permanganate is actually equals to 0.020 by 0.000, which is equals to 2.00 times 10 to the power of just let me punch the calculator again. 0.0, okay, sorry, 2 times 10 to the power minus 4, okay, moles. Okay, then from here, what we are going to do is we need to determine the number of moles of electron transferred. Okay, I think you have seen a lot of permanganate equations. If you have forgotten, let's go back to it. Yeah, so permanganate will take in 5 equivalent of electrons. So if you understood this, from here you can calculate the number of moles of electron transferred. Okay, transferred. Okay, this will be this number multiplied by 5. Okay, 10 to the power minus 4 times 5. Okay, so I'm going to end up with 1.00 times 10 to the power minus 3. Okay, times 10 to the power minus 3 moles. Okay, and then what we're going to do is we'll take the ratio of ethane diolates to the number of moles of electrons. Okay, number of moles of electrons. So the ratio will be by ethane diolate 5.0 minus 4. So that will be 2:1. Okay, so that will be 2 is, sorry, it's the other way around. What am I talking about? Yeah, so maybe in order to prevent making mistakes, let us just write it out first in order for us not to make any mistake. Okay, okay, so you get 1:2. Okay, so therefore each ethane diolate loses 2 electrons. So 2 carbon loses 2 electrons. So each carbon loses 1 electrons. Okay, so from here you can tell that each carbon in C2O4 2- loses 1 electron. Okay, the oxidation state of carbon in ethane diolate is +3. Okay, we can easily verify it by letting it be x, so 2x minus 8 equals to -2. So x is equals to +3. Yeah, so after losing 1 electron, the final oxidation state of the product will be +4. Yeah, then possible identity will be CO2. Yeah, you notice that the question did not give you the identity of the product. Yeah, it's actually for you to suggest the nature of the product, so that's fine. Okay, so I hope you roughly know what is going on, although it's a bit messy, but along the way, I think I verbalized the thought processes, so I hope you have a clearer understanding of what happens. Okay, finally, we are at exercise 4.8. So we just jump straight in. So in a redox reaction, 1 mole of thiosulfate is oxidized by 4 moles of chlorine. So which of the following is the sulfur-containing product in this reaction? Okay, so again, we need to understand that when chlorine behaves as an oxidizing agent, itself will get reduced. So you will take in 2 electrons, and then you will get 2 Cl minus. Okay, so if you are not sure, again, data booklets. You can always look at the data booklets. Information is given here. Okay, so it's over here. Then after that, you were told that 1 mole of thiosulfate is oxidized by 4 moles of chlorine. Yeah, so that means that what I can do here is I will just multiply this by 4. So if I multiply this by 4, I will get 8 electrons. So 8 Cl. So that means that 1 mole of thiosulfate gains 8 electrons. Okay, then that means each sulfur will, sorry, not gains 2 electrons. What am I talking about? Loses. Each S2O3 2 minus loses 8 electrons. Okay, then each S2O3 2 minus have 2 sulfur. So therefore, each sulfur will lose or loses 4 electrons. Does that make sense to you? Okay, so each sulfur loses 4 electrons. Yeah, because one species of S2O3 2 minus loses 8 electrons. Yeah, one way you can go about doing that is you can just write this out. 2 minus is to number of moles of electrons. So this will be 1 is to 8. So each sulfur will be 1 is to 4. Okay, then the oxidation state of sulfur here, okay, of sulfur, you can easily determine it. So it's 2x minus 6 equals to minus 2, 2x equals to plus 4, x is equals to plus 2. Yeah. So each the sulfur's original oxidation state is plus 2. So if sulfur loses 4 electrons, the final oxidation state will be plus 6. So final oxidation state is equal to 6. So basically, we just need to look out for the oxidation state of sulfur to be plus 6 in all these species. So you can do a quick calculation. So this is 0 here, this is plus 4, this is also plus 4, this is plus 6, and then I think this is plus 2. Yeah, so only one answer fits, which is sulfate. Okay, so the final product is likely to be sulfate, or it has to be sulfate because that is the only one with a plus 6 oxidation state from the list given to us. Okay, so my parting message for you for stoichiometry would be balancing redox equation and balance equation, which essentially involve mass balance and of course charge balance. They are very important ideas, and it's actually important in all aspects of chemistry, not just redox or practicals. When you move on to advanced topics such as acid-base equilibrium and even energetics or electrochem, or in your future university education are very important. So I hope you benefit from this particular lecture series on stoichiometry, and having understood all the ideas, you should be able to apply them, and hopefully you will find that your road ahead is easier. Remember that stoichiometry requires practice, and do spend more time on thinking about processes in getting the answers rather than keep doing without thinking. Yeah, in most cases, you can understand what is going on simply by thinking along the line of electron transfer. That should fit everything. Yeah, so if you enjoy listening to the video, please do subscribe and then write comments below. Yeah, and then press the like button if you wish to.